Hey, good morning, everyone. Thanks, Operations, for playing the intro video. My name is Adityan. I also go by Adi, and I'll be taking the stream processing class for today. Let's go over the agenda briefly, and I can introduce myself as well, and then we can get started. Just a moment, just pulling up the participants window here. Yes, go ahead, Gayatri. Wants to make an announcement.
Thank you, Adityan. Hi, everyone. Good morning. This is Gayatri from the Student Success Advocate team. Well, today being the last class for the system design module, the system design program feedback form is now live on your UpLevel account. Therefore, I would request each one of you to kindly share your valuable feedback on the system design program feedback form. Thank you so much. Thank you, Adityan.
Thank you, Gayatri. Okay, so a quick introduction. I come with 5+ years of experience in data engineering and ML engineering, having worked at companies like Amazon, Udemy, Poshmark, which is an e-commerce marketplace, and bunch of other internships in the US. Went to Georgia Tech for grad school, and my association with IK has been over 1 year old now. I teach the system design, the live stream processing class, as well as some data engineering modules as well. And what motivates me to be here today is I love mentoring, coaching, and kind of being your thought partner in your interview journey. I've interviewed extensively for myself in the market in the past when I was looking for jobs, and I also take interviews for different candidates at the companies I work for. So I can happy to share any relevant insights from those and just be a part of your career up leveling and progression as well. This class will be a stream processing class. What it means is, let me set the agenda for today. It is a system design class, but it will be a very technically intense class on designing real-time systems. So we will focus very heavily on real-time systems in this class. I know there are other modules in IK for batch and online system design. And those modules will cover aspects of system design which may not touch on the real-time components. We would like this class to be like a specialist class on real-time system design. Having said that, it assumes no prior knowledge. We will try to keep the class as beginner friendly as possible. Even if you don't have any experience in real-time systems, hopefully you'll get to take something away from the class. And if you're already an expert in real-time processing systems, please bear with me for the first 30 to 45 minutes. It might be too elementary for you, but I promise we will have deep dive discussions on good technical topics going forward. Our interview case study will be design Datadog. That will be the case study we will go through in this class, or generally any application monitoring tool. And I have a brief video on what Datadog as a tool is in case you haven't used it. We will introduce the tool and its functionalities and generally talk about application performance monitoring tools and how we'd go about designing such a tool. We will study distributed queues as a primer. So the first section of the class, our first two sections of the class are going to be studying the architecture of RabbitMQ and Kafka. So we will deep dive into the architectures of these two distributed message brokers, pros and cons, why some things are the way they are, which is a better product in what use cases and whatnot. And the point of studying distributed queues is so that we can apply that domain knowledge and best practices to going back to our interview question, which will be a bulk of the discussion of the class. We'll spend about 3 hours designing a Datadog like solution. That's the agenda. We will have 2 breaks in the class. We will have a 10-minute break at some point at the 1 hour mark. And we'll also have a lunch break around, we'll try to time it around 12:30 Pacific time, so you can plan accordingly. And we'll keep the class interactive, and feel free to bring your questions, feedback, use the raise hand feature, and can bring whatever thoughts you have to the class as well. That's the agenda for today. Any questions on the agenda before we get started? Okay, great. Let's get started. Like I said, the first 30 to 45 minutes are expected to be a quick primer. So bear with me if this is introductory. We'll scale up gradually. Just getting everyone on the same vocabulary and the same page on distributed systems in general. So let's talk about large scale systems and kind of just segment large scale systems into online, offline, and real time systems, and just talk about what these systems entail and how to classify certain interview questions among these patterns. So any large scale system these days is a distributed system. And by distributed, it means components are geographically distributed. Geographically apart. So you may have many components, databases, compute, memory, cache, storage. All those things may be geographically in different locations and whatnot, which exposes a lot of challenges while designing large-scale systems. But this is pretty much a necessity now. Any system you interact with will be need to be built as a fault-tolerant system that will kind of be available all the time, recover from failures automatically, and so on. Examples of large-scale systems include your classic URL shortener example, Bitly, ride-hailing in Uber and Lyft, and many other day-to-day apps you use. Each of these systems will have CPU, memory, and network at different layers in the geography as well, and each component will be having multiple of these. So we'll talk about Apache Spark and so on as well in the class, and we'll talk about what that means. So one thing to keep in mind is these days when we build any system, the input to those systems is extremely large. And by input, I mean any data that your system is ingesting or crunching through. We no longer live in a world of small data or anything. We live in a world where data by nature will have millions of rows, gigabyte and petabyte scale data, and so on. The output of your systems is also large data in most cases. You'll have a lot of rows that are computed and churned through and eventually get written to a database or your data lake like S3 and so on. To do such a computation, it's common to have what's called a batch computing framework or batch processing, which is examples like Spark is the most popular one. Let me also put MapReduce here. So what it means to do batch processing is you have an extremely large task of scanning through millions of rows and doing something with those rows. You don't do those in one machine anymore. You break down the big task into smaller manageable tasks, and you ship that task or work out to individual machines who will work on those smaller tasks. That's what a batch processing framework does. And Apache Spark is the best known example for such a use case. Having said that, we have kind of a classification or a mental model to follow in terms of how we design systems. We have the notion of online, offline or batch, and stream processing systems. Let's briefly talk about behavioral characteristics of these systems and some examples what may fall in these categories. There is a module for each of these in IK. We are in the stream processing module here, but let's just briefly think about what does it mean to be an online system. An online system is usually something along the lines of a request response type of system, where your expectation of the system you're building is kind of interactive in nature. You do some actions, you hear back from the system in some quick turnaround time, you do some more actions, and so on. So such systems may be architected as a request response system, and online systems fall under such category. Batch systems, your response or actions don't need to be instantaneous. So what are some examples of batch systems? You interact with a system and you get curated emails, let's say marketing emails or push notifications. Once a day, you get push notifications advertising something, or you go and search for dog products on YouTube and you get some push notifications from relevant channels and whatnot once a day or once a week. Those are kind of batch systems. The goal is to capture the user, bring the user to your website, but not annoy the user by sending too many push notifications or something. And in general, how such systems work is they crunch through a large amount of data and prepare something that needs to be sent out or worked on. In this case, emails and push notifications are one example. Stream processing system, which is what we'll talk in the class, what the characteristics of such systems are: data is always moving. So there's usually data coming in. There's some kinds of producers sending data, some kind of consumers working on data. But essentially, your expectation out of a system is you act on data, which is the important part, act on data instantaneously. Or you can say real time or near real time, whatever you want to call it. So the point is you have incoming data, and your expectation of such systems is you're going to do something with that data, perhaps make machine learning predictions, like let's say credit card fraud checks. You have new data, which is your transaction, and your expectation is you'll classify that transaction as a fraud or not. So you're acting on new data immediately. Those kind of systems are stream processing systems. There's a very thin line of difference between online and stream processing systems. In general, how I would think about such systems to be is stream processing has large amount of data moving, and generally such systems are not reliant on needing accountability or guarantees for all the data, which means unless you are building something like fraud or something related to financial transactions, you have the notion of fire and forget in such such systems, which means you have so much data, you build such systems to handle the scale of incoming data, but not necessarily enforce guarantees that every record should be processed or should be kept with integrity and so on. Online systems may be closer to where you need higher guarantees of data, and maybe the patterns these systems follow will enforce more kind of asset compliance and perhaps guaranteeing that each record is successfully transacted on and so on. They are consequences of what we expect out of online systems. So let's look at some more examples of stream processing systems, and we can open it up for some questions. So as we talked about stream systems having
do you mind if I ask you one question?
Sure, go ahead, Rishikesh.
Hey, can you go back to the previous slide?
Mm-hmm.
Yeah, so here, when you said like online processing is simple request and response, correct? And then the batch processing is where you would like process and keep stuff ready. So that way, whenever the API hits, we can just give them the response.
Right.
Correct? So in the streaming processing, and I don't want to confuse it with like, you know, the streaming of like Netflix and YouTube and stuff like that. But I think in general, what you're saying is there is always some data that is captured either from the user and or the server, and then there is always some data in transfer that is happening, correct? Either a request or a response that is always happening. Okay. So in that case, right, like one important thing, right, I mean, let's just assume a system where we are making like uh, where there is like a lot of data being exchanged, right? So for example, a bank account or something like that, will that be a streaming processing or will that be a batch processing or online processing?
Yeah, great point. So it's kind of, I would say it's not exactly clear on how you implement such systems, though if you are always kind of querying data, it is not to say that you can't architect a bank system like a stream processing system. You could architect it using a stream processing system. In fact, things like market brokerage firms with stock market feed and all, they are actually streaming systems, but they have higher guarantees of data. They just do better making sure all the data is accounted for. So bank processing systems could be streaming systems, but you want the additional capability that you will make sure to build it with guarantees in the data that is coming in. You could build it as online systems as well if streaming systems is an overkill. So it kind of depends on how you architect it, but you could do multiple ways there. Also, one thing to notice, any system could have multiple sub-components, which may be batch systems, online systems, and stream systems. So a bank system could potentially have some components which are batch processing, some which are online, and something which is streaming as well.
Okay. Yeah, that's what I was getting at, is like we can have a system. I mean, bank was like just an example, but like we can have a system with a multiple processing, right? Like batch and stream or online and stream or something like that.
Exactly. Yes. Exactly.
Cool.
Yes.
Thank you.
Great question. Divakar? I think you're on mute, Divakar, if you're saying something.
Yeah, sorry. I was on mute. Actually, banks, the data which banks and stock market uses is a structured data. So the data was like in it would be in a tabular formats. The transactions are all in structured data. Say, for example, if any person withdraws some money in ATM, it would be reflected in very real time processing. So whereas most of the data is completely structured, which banks uses mostly the distributed data systems, database systems. Yeah. So whereas online streaming could be like messages, queues, any videos, streaming, everything can be used through Kafka. But I mean, this whatever the online streaming could help is not only structured, it could also help us to use unstructured data like Google data, search data, or anything. Yeah. So that's a major difference is how the banks are stock markets are using, since the data is structured and unified. Mostly they use like SQL databases and use like online OLTP transaction systems, mostly are distributed data systems.
Great. Thanks for sharing.
Yep.
Sounds good. So yeah, great discussion. We can look at some more examples of streaming systems, but one other thing to notice, we will talk a lot about queues or message brokers, but by no means should we just think that if we use a queue or message broker, it makes a system a streaming system. It does not. You could have a queue or message broker in a batch system or online system as well. The bigger idea here is the nature of the system, which classifies them as online, batch, or streaming, not the choice of components that you use. Having said that, let's look at some streaming examples out in the market. So we already have incoming data and you want to process data in real time. You have multiple downstream systems that depend on your data feed. So you can have things like recommendations, personalization going on, some machine learning going on and whatnot. So some examples of streaming systems. Datadog, which will be our case study today. But in general, any application performance monitoring tool can have streaming, is built on streaming capabilities. There are other products like New Relic, Prometheus, AWS, CloudWatch. So just laying out other products competing with Datadog. If you've used any of those, they have the idea is you're monitoring a fleet of infrastructure in your company. You're monitoring system health metrics, some custom metrics. You have logging, you have alerting. You graph all those things. You provide a user with a real-time graph and so on. All those tools are built on the premise that you are going to learn about your infrastructure in real time. If a server goes down, you want to find out in maybe 5 to 10 seconds that the server is down. So they are built on capabilities of real-time systems. Fraud detection. There is a popular company gaining traction these days, Sift Science, but there are many other companies. You can kind of send them a feed of your transaction data. They'll tell you in real time, is it a fraud or not, and so on. These systems will have real-time components in it, perhaps online components as well. Algorithmic trading and stock market surveillance. We already talked about it a little bit, but anything that ingests data in real time, like news data, Twitter, trending data, and so on, perhaps some price related data, Fed's report and all that, and it'll crunch all that data in real time and make trades for you. So such systems will have real time capabilities. Trend detection in Twitter would be a real time system as well. You're kind of bubbling up what's trending in the world up to using hashtags and whatnot up to the audience. IoT systems, Internet of Things, Nest doorbells, ADT cameras. These have capabilities which are real time. So you have person detection, animal detection. Someone in your backyard, if you spot movement, you get a push notification instantaneously that there's an animal in your backyard or something. So those systems are all real-time systems because they are acting on a feed of video incoming and making predictions. Saved searches on Zillow or Redfin, these could be closer to offline or batch systems. I have it here, but think about why they may be batch or batch systems and perhaps not close to real-time systems, because the housing inventory around your area might be in the few thousands. So you're really transacting data that's not millions of records, but closer to thousands of records, and even lesser with your criteria and so on. So perhaps you could architect. Yes.
Sorry to interrupt you, Aditya. Can I ask one question on this?
Yes.
So how can this be a stream processing system? Because technically, what I envisioned is in Zillow, right? Like you will have a lot of data which will be probably stored and like probably batch processed, right? And then whenever a user does a read, right, a user, that means an end user coming in and like just trying to query and say, hey, can you give me all the homes that are available for sale in this particular zip code? Then you'll just do a read and on the index data and you will show that. So why will it be a stream processing? There is no data that is coming in and going out live while the user is interacting.
I agree. Yeah, that's why I was just correcting it here. So Zillow, Redfin systems would be closer to batch systems.
Okay.
You could make them a stream system, but that may be an overkill for the use case and may not be the best way to do such systems. But you're right. So there's less data, and you can get away, or perhaps you don't even want to do a streaming kind of architecture here. You can do a architecture where you get some records, crunch them, and send to the user, and they are all computed in batch. And housing inventory is updated at some cadence. Maybe they all feed into MLS, which is where all the housing market data comes from. But yeah, those may be closer to batch systems in some capacity. The last example is activity tracking, which is very popular, and we may talk about this through the class as well. If you've heard the term clickstream pipelines, these are very common now. Few years ago, they were capabilities that companies built in and got competitive edge, but now it's almost like a necessity to have. What it means is, you on a social media web page, Instagram or Facebook or whatever, you have content. As the user clicks or views or does any action, scrolls, or even dwells on a post, like if you give a post eyeball time for longer than a couple of seconds, it shows interest. So the point is, when you do such actions, they are tracked and they all go through some eventing system, which is what a clickstream pipeline is. So all your actions are tracked. They all feed into some kind of storage where you will then get personalized content or get targeted with ads, recommendations, search improvements. Perhaps your data will get sold and whatnot. But the point is, such systems are real-time systems, and they form the backbone of a lot of social media companies. Okay, I see some questions. Karthik, do you have something to ask?
Yeah, I think it might have we might have discussed earlier. Just one liner. Where would this Netflix, YouTube? Because it's like stream buffering and all, right? Would it fall under stream processing, or would it fall under any other category? Can you?
Yeah, great question. So I wouldn't think of video stream. I wouldn't confuse video streaming with stream processing systems. Video streaming may include things like serving the video with CDNs and whatnot close to the user. That being said, there will be components of a YouTube or Netflix which are streaming in nature, like real-time recommendations. You search for a movie, you go back to the homepage in Netflix, your recommendations are reflective of what you just searched, and so on. So those may be streaming systems, but the video streaming capability itself may have streaming capabilities, online capabilities, but I wouldn't want to confuse video streaming with stream processing itself.
Okay, thank you. Yeah, it makes sense now. Because I think the video will be cached nearby to the edge locations, and from there Now, how the buffering, I don't know, it's a separate topic, but they also have this separate buffering. The data keeps on coming in buffer. So
Right.
it is basically the mechanism using, but it won't be called a stream processing, but it's a protocol within that streaming itself, right?
Correct.
It's a protocol.
Yeah, exactly. Great point. Let me ask Syed first and then Divakar. Sorry if I mispronounce anyone's names.
Thank you. So I just want to know if you already finished the list that you're showing here to basically categorize them based on online batch or streaming. Did you finish that yet or not?
Yes, this is the list, and we'll be moving forward.
So
Yes.
my question is, the trend detection is batch processing. Am I right?
So you can have batch components, but so would you have real-time components like ingesting data from Twitter or news articles? That those components may be real-time components. You're always ingesting data and kind of bringing out trends in the data. So they will be real-time streaming systems.
Because the way I'm thinking about it is, as you mentioned it, we have an online system. It keeps track of the logs basically. And then we have a batch processor, let's say every 5 minutes or every 10 minutes, it goes through the logs and just, for example, group by them.
Right.
Is this the way it works?
That's definitely a good proposal. That's one way it can work. And in that case, what you're doing is you're running a batch process every 5 minutes and so on. Perhaps when it becomes a streaming system is when you do the same process at a very low cadence, like perhaps every 2 seconds to 5 seconds. Then you can call it like a streaming nature. But if you're doing every 5 to 10 minutes, you're computing data, that may be closer to a batch system that just runs more frequently.
Actually, that was a very good point I wanted to ask. Even if I have a batch, it runs, let's say, every second, every millisecond. But in nature, it's still a batch processor, but you call it the stream processing?
Yeah, great point. So yeah, you're coming to what is a true streaming system versus micro batch system. So for our use cases, we'll talk a lot about Spark streaming, which is exactly what you're talking about. It's essentially batches of data, but the batch of data is extremely small. So perhaps 1 second interval of data or 5 seconds worth of data. And it's a micro batch that is worked on. So at the end of the day, Spark is a batch processing framework that gave you the real-time capabilities through Spark streaming. There's something called Flink and things like that, which may be closer to true streaming or a replacement of Spark. We may not talk about those in the class, but that's how the most popular industry offerings are built. They are, at the end of the day, computing on batches of data, and the size of that batch is so small that it makes it a real-time system.
I see. I'm trying to learn the terminology basically, because in your last slide, you had 3 categories. So micro batch processing falls under streaming processing in terms of like interview vocabulary.
Correct. Yes.
Awesome. Thank you.
Yes. And we'll talk about this in detail shortly. We will talk about Spark streaming and how micro batch processing actually works. But great point.
Thank you.
Okay, great discussion. Divakar, I saw you had your hand raised. Maybe it got answered. If not, feel free to let me know. If there are no questions, I would like to introduce the interview problem for today. Let's just look at this and then we can dive into the next section. One moment. Okay. So we don't need to watch the whole video, but just a few minutes.
Datadog is an infrastructure monitoring service. It empowers DevOps teams to keep tabs on dynamic cloud environments. Datadog makes it easy to visualize the health of your infrastructure at a high level by location, application, or service. You can also view it on a more granular server-by-server level. The first step in setting up Datadog is using a combination of the Datadog agent, our API, or our integrations with third-party applications and services. At the time of this recording, we have over 120 integrations, and we're adding more all the time. The Datadog agent can run on cloud platforms, bare metal servers, virtual machines, containers, and more. Perfect for customers with cloud or hybrid infrastructures. We support the agent on all major operating systems. Deploying and managing the agent and integrations may be done through automation tools like Chef, Puppet, and Ansible. The agent collects system-level metrics like CPU utilization, disk I/O, network latency, and more at a resolution of 15 seconds. Using other methods, we can collect metrics down to 1 second resolution. The agent is resilient to network outages by retaining metrics during an interruption. Metrics are later submitted and backfilled once the network is back online. All communication to Datadog is over HTTPS using port 443, and traffic is outbound only. The Datadog agent is entirely open source, meaning it's easy to dig into the code and find out how it collects metrics. Just navigate to the checks.d folder to see all the Python scripts responsible for collecting.
Okay, so just wanted to introduce what Datadog is as a precursor to our interview question. Let me just briefly explain it for anyone who's not used the APM tool. Karthik, do you have a question?
Sorry, one quick question. Sorry, it was for the previous slide. Regarding that Spark streaming, just one quick question. I don't want to interrupt on it. But Spark streaming, right? You said it's a micro batch processing, which means that does it takes 5 seconds micro batch then puts it. So is that what? So it takes 5 seconds. It will wait for it, batch data, and then stream the data, right? That's what you said, right? Spark
Correct. Yes, that 5 second is configurable. Whether it's 5 or 1, it's your choice, but it will do some form of micro batch processing.
Actually, I wanted to check what is it in comparison to Spark streaming that Amazon Kinesis streams are also there. So is it different? Kinesis, it actually takes real-time data, but why streaming would be popular choice compared to Amazon Kinesis, or both are like the same thing? Only it's that Amazon is offering it. That's what my question was.
I see. Yeah, I think so. How I see it is Spark is potentially older and open source as well, and it's kind of vastly implemented in many products, as well as Amazon also offers Spark packaged offerings. There are just pros and cons, and these Kinesis is closer to a broker. Spark is streaming is not a broker. The closer comparison you can draw is Kinesis versus Kafka is a comparison you can draw. So those are queuing technologies which kind of hold your data in transit as well. Spark streaming is a compute technology. So its job is not to hold your data, but more like produce or consume the data. So where you would use it is you can use Spark streaming with Kinesis, for example, where Spark streaming produces data. Like Spark streaming will produce data and send it to something which can be Kafka, Kinesis, RabbitMQ, whatever you use here, and then somebody works on the data, and that can also be Spark streaming. So that's how I would view it. It is more of a technology which is responsible for ingesting data, doing something with it, or working on data that is coming in and doing something with it. The queuing system or message broker is what Kinesis, Kafka, RabbitMQ, and many other technologies are. Their job is to be the middleman between your producer and consumer. So it will transfer the data, do bookkeeping of the data, life cycle of the messages that are coming in, delete data once it's read, store the data permanently. All those kind of things are what message brokers do. Hope that makes sense.
Yeah, thank you so much. That clarified a lot. And thank you so much.
Great. And we'll revisit this shortly. We have a whole section on Kafka, and we can talk about different terminologies there. But briefly introducing our Datadog question for the day, so that all of us are on the same page. What is a APM tool? With the YouTube video you just saw, where do you use a APM tool is, let's say you are Amazon and you have many servers in your department. You have a order server, payments, you have recommendations, search, video, Prime Video, audio, all that stuff. Now you have thousands of servers, or perhaps 10,000, 100,000 servers at Amazon scale. How do you monitor the infrastructure health of all your servers? How do you know what is the CPU utilization by time? How do you know memory utilization by time? And perhaps you want to know custom metrics as well, like how many orders were processed, how many orders were processed in this server, how many payments are declined, and so on. Many custom metrics. So how do you learn about these metrics, track them in real time? That's exactly what an application monitoring tool does. So it provides you the framework to do this. And the point of a tool like Datadog is to gather those metrics from all those servers. It will gather system metrics like CPU, RAM utilization, network upload, download, all those metrics. Plus, it allows you to gather custom metrics, which you as the engineer define. So you'll define orders processed, payments declined, and so on. You will define all those metrics. You'll define what they look like, the schema of the metric, definition, all those things. What Datadog will help you do is it will help you transmit those metrics in real time and then collect it somewhere, perhaps aggregate it, process it, and eventually surface such a dashboard tool for you, which you can use to monitor. Then you can have things like alerts set up. So if you can have things like, if CPU is above 80%, send us an email or Slack notification. If CPU is maxed out, call an on-call engineer, send an alert through SMS or pager duty, some alerting mechanism, and so on. So it provides you a host of functionalities, but the crux is its job is to integrate with your ecosystem and tell you everything that is going on in your ecosystem. So what we are designing today is this product itself. We will try to think, how will we design a product that integrates with your ecosystem and tells you all the things you need to know. We have some specific criteria, and I know there are questions. So let me just lay down the requirements for the question for the class and then take some questions from all of you. So the prompt is, imagine a data center having 10,000 servers emitting 2,000 metrics a second. Every second, each server emits 2,000 metrics, and 2,000 metrics can include things like CPU utilization, memory utilization, and a bunch of custom metrics that you are free to define. But we have a limit of 2,000 per server per second. Given that, design a central brain that ingests and serves a dashboard. So you will query this using certain query paths. So one way is, given a server ID, tell me the min, max, average across all metrics in a time window of 2 days at a granularity of a minute. What that means is, anything that happened to CPU utilization in the last 2 days, I want to know minute by minute what the minimum, maximum, and average of that CPU was in any server by minute. Similarly, given a metric ID, return min-max average across all servers in a time window of 2 days, granularity at a minute again. And we have some time range queries. So given a server ID and a time range, which can be like 2 days, 5 days, 3 months, return min-max average across all metrics. And given a metric ID and a time range, return min-max average across all servers. And we will have data living for 1 year. So that's the official prompt. You can see this question in an interview without such a detailed description. They may just tell you design APM tool or design Datadog, and your job might be to kind of clarify and come up with some hard requirements. But we have a specific criteria. We will be designing our solution in the class today. Let me pause here. Deepak, do you have a question, comment?
Yes, Adityan, thank you very much. I have two questions. First is Datadog. Like there is a tool you mentioned, Prometheus, right? Just wanted to know, between Datadog and Prometheus, I have seen Prometheus used a lot in MLOps kind of setting, but I haven't seen Datadog. Like, do you know that Prometheus and Datadog, what are the differences, and like which use cases one would use one versus the other?
Yeah, that's a great point. Actually, I have never had a chance to use Prometheus so far. I've only been using Datadog and all the companies I work for, including for work related to MLOps and things like that. So I don't really know much on what the technical differences are between Prometheus and Datadog. Perhaps someone who's used Prometheus can add insight there. But I do know it's also a competing product. I would imagine there are some functional differences, maybe how things happen underneath, and maybe some features are also different and so on. But I don't know for a fact right now.
But in the rough, they both sound like similar APM kind of tools, right?
Yes. That's
okay. And second question is regarding this statement here, this problem statement here regarding Datadog. So you said data will live for a year. So when we say data will live for a year, are we talking about the second by second data, or are we talking about the compiled data at a 1 minute frequency that will live for a year?
Great question. Let's just say compiled data. Second by second data will maybe way too much data to store for a year. So let's say compiled data, 1 minute aggregates should live for a year.
Okay, thanks.
Okay, great clarification questions. Kaviraj?
Yeah, my question is like, is it similar to the ELK stack which we have, where we have this agent which pulling this server information, also the custom queries which we have defined. Based on that, it creates the matrices, or also similar to Splunk, where also we can see we can create dashboards. So is it similar to that, or because I'm just thinking because even APM tools, most of the cloud services, they provide the APM tools to monitor your instances, right, or the servers. So why do we need an additional to like Datadog, which is the additional thing which we get from this kind of tools, right?
Yeah, this is a good point. So yes, Datadog is somewhere similar to Splunk, perhaps also similar to ELK stack. For those of you who don't know, ELK is 3 different components: Elastic, Logstash, and Kibana. I'm maybe misspelling the E part, but there are 3 kind of things there. Logstash is your producing agent, something that produces metrics. Kibana is your visualizing, graphing tool that will help you visualize everything and things like that. Why do we need Datadog is a good question. So it is a product that integrates well with many parties. cloud vendors, servers, physical servers, and so on. And it provides you many capabilities like alerting, anomaly detection, and whatnot. And perhaps it's built for performance and stuff. So the point is, it is a tool that competes with many other tools, like you mentioned, and like every tool has some edges over other tools, perhaps cost and things like that too. Datadog is a very popular tool, as far as I know. Many companies make use of it. Why do you not build something just in-house or just use something that's already installed? You can, but Datadog is generally available across different stacks. So you may have a wide variety of infrastructure in your like company, and a central tool that is capable of integrating into all that infrastructure will kind of help you monitor things and kind of have a high level overview of what's going on in your system. So it's a popular tool. A lot of SRE teams, infrastructure teams make use of as well.
Okay.
Some companies make
you
use of
mentioned-
Faang, Prometheus, and things like that too. So it depends on what your company chooses for your use requirements. So Datadog is just one example. By no means am I saying we are only talking about Datadog. We can just generally think of designing a tool that will help you do application performance monitoring.
Okay, and in our functional requirement, we are not considering the custom queries or basically the custom matrices, or are we still considering that as a functional requirement?
Yeah, great point. We are considering those. So part of the 2000 metrics is your system plus custom metrics. So you want to think, how will you design something that will handle both?
And the notification service, that is also
we can leave
functional
out
requirement.
notification. Great point. We can skip notification, alerting, those services for now. We can just design the central backbone first, and then we can talk about those extensions if time permits, but those are not part of our first requirement.
Okay, thank you.
Great. Karthik, do you have a question?
Oh, no, sorry. This was my. I think I didn't lower my hand. Yeah, I didn't have any questions.
Okay, sounds good. Rishikesh.
Hey, so when the question says all metrics, what are the metrics that they are like specifically talking about? Is it like some assumption? I mean, we can just assume certain metrics, or is it like something that is predefined in this question?
When we say all metrics, we can say all the 2000 that belong to a server. So for this thing, we will say all 2000, because a server is expected to produce up to 2000 metrics. It may not always be 2000, but let's just standardize it and say there will be 2000 metrics available. Sometimes a server may not have 2000, it may just have 1000 or 500 metrics available, but we are building the capability should handle 2000 metrics. And all servers will just include 10,000 servers. So given a metric and time range, if you query, you want return min max average across all the 10,000 servers.
Yeah, but like an example of probably metric is like, I'm just making this assumption, right? Like successful logins, right? That is one kind of a metric, correct?
Yes.
Yeah, okay, cool.
Great point. So successful logins, and we talk about some of these here. So similarly, custom metrics, examples of custom metrics in the case of Amazon or any e-commerce site might be orders processed, payments declined, payment successful, shipping label, number of shipping label created, number of shipping label invalid, all those kind of things. Yeah.
Cool. Thank you.
Animesh?
Yeah, I was thinking like for these kind of questions, should we think about security too, or can we assume that it'll be in the private private, what is it called, subnet, so that we don't have to worry about security? Or should we think about how the client would be communicating with the servers?
Yeah, great point. We can assume security is a given through some secure protocol. Bulk of the discussion will be more around designing event-driven real-time systems, so we can leave out aspects like security or designing. We will focus on the real-time technical discussion involved in this.
Sure.
Security can be a question that comes up in your interview, but won't be something we'll discuss in the class today.
Okay. And the database, like I got exactly the same question in one of my interviews. I proposed the time series database, the InfluxDB. Are you going to think about the DB too in the background? Like what kind of database you will have in the background, or are we just going to say, I don't know much about Kafka or other streaming processing, so maybe I can ask this question later on.
Great. Yes, so we will talk about databases as well. We will reserve the last discussion will be on some databases and something around time series and so on as well.
Thank you.
Great points. So let's get started on the next subsection. What I wanted to do with this was just introduce the problem so we know what we will work on shortly. But before we dive into designing the solution itself, let's take a step back and study distributed queues as a primer, and then we'll use those things in our discussion for Datadog. So what I want to do next is we have two agenda topics, RabbitMQ and Kafka. We'll study them technically, deep dive in them. We'll study RabbitMQ first and then take a short break and then come back and study Kafka next. Okay, so distributed queues or message brokers. There are many technologies that are available in the market. We will talk about patterns and then perhaps extend them into actual products like RabbitMQ and Kafka. So on a high level, there are two patterns these queues follow or message brokers follow. So there is a class of in-memory queues where messages are stored in memory. There is a class of queues which are disk-style queues where messages are stored on disk. RabbitMQ falls under the in-memory style of queues. Kafka falls under the disk style queues. What does it all mean? So sometimes you need the ability to kind of transact messages extremely fast. So style of queues that enables such decisions is the in-memory class of queues. They are very well known for very low latency message delivery in the order of few milliseconds. In-memory class of queues is generally needed in some requirements where even few seconds level of latency is too slow or too late. You can think of it like algorithmic trading systems or something like that may actually have in-memory queues as opposed to disk style queues. Having said that, there's few more things. RabbitMQ comes off is a implementation of what's called AQMP. That's Active MQ Message Protocol. What it is a protocol of how to build a message broker. RabbitMQ is the most popular open source offering. RabbitMQ is packaged in AWS. There's AWS MQ. Amazon MQ is a service that gives you RabbitMQ off the bat with all its functionalities. It's a bit of an older technology. It borrows some ideas of what's called a smart broker dumb client. We'll talk about what it means to make a broker smart and what it means for a client to be a dumb client. It supports things like very low latency message delivery, which is a consequence of storing messages in memory. Supports things like complex routing and priority-based delivery. Priority-based delivery, a very crude example is you have messages in your queue, and usually you would expect messages to be processed in first out order. But sometimes you have requirements where message M2 is more important than M3, more important than M1. When would this be the case? Think about telecom customers. Maybe you are designing the message broker for transmitting messages, and you have multiple clients like AT&T, T-Mobile, Sprint, and whatnot. Now, some of these bring in more dollars than others. And by contract, you have to honor those customers' SLAs over the lesser important customers and so on. Perhaps AT&T gives you the most dollars and Sprint gives you the least dollars and so on. So you prioritize those messages. Maybe you have the message being transmitted in your broker comes with some field. Maybe you can infer the priority or who the message belongs to. And anytime there's a message from AT&T on Sprint, you make sure the AT&T message is first taken care of, and then the Sprint message gets taken care of, and so on. So just an example of a priority-based delivery. We'll talk about how RabbitMQ enables priority-based delivery. RabbitMQ started in a world where elastic compute was not as widely known as today. So there are some limitations from where it started. It's been solved for in more recent versions, but it was initially architected to be scaled vertically. And you can think of it like if you store all the things in memory, one obvious way to scale up your message broker is to scale up with a bigger machine size. That is no longer true in the recent versions anymore. You can horizontally scale RabbitMQ. There are a few more things. RabbitMQ works best when queue lengths are small and message ordering is not guaranteed. And we'll talk about this once we talk about the architecture itself. But let's briefly touch on basics of RabbitMQ. So any queuing or message broker has the notion of a producer and a consumer, or a publisher subscriber, whatever you call it. Producers are agents that produce messages, or it can be code as well, like your backend code written in any language of your choice is actually a producer in some ways. So if you write some service in Java, Python, Ruby, whatever, those can act as producers. There are logging agents which are producers, like FluentBit, Logstash. Someone talked about Kibana, Elk, and all that. So Logstash, what these are is effectively, I'm giving you real life examples of producers. These are basically tools. What they do is whenever you have some server or some service running, you will have some logs generated. There will be some tool that kind of tails the logs, looks at new records coming into the logs and funnels them into your queue. So those are producers at the end of the day. Messages themselves are data in flight. Message can have a payload, a header, and it can look something like this. It may have some header which will tell you some metadata about the message, where it's coming from, where it's intended to go to, all that stuff. Payload will be some key value structure here. So it will have some structure to it, field A, B, and so on, some values to those fields. That's what a message looks like. RabbitMQ has the concept of routing keys and exchanges. We'll talk about that in the next slide. Queues are the entire RabbitMQ container itself. So queue will have many things underneath it, which will be clear in the next slide. Consumers are your end entities, or code, services, apps, whatever you want to call it. The job of a consumer is to read messages of your queue and act on those messages. So you can have many kinds of consumers. You can have things like recommendations, any service that personalizes your content based on some incoming data is a consumer. You'll have search keywords or something. Maybe the autofill on your search bar is a consumer at the end of the day, because maybe it is gathering data, plugging in data from some other sources, maybe your past searches, how you're interacting with the website, what you're typing in real time, and then it's informing the choice and populating your drop down. That's another example of consumers and whatnot. So you'll have many kinds of consumers. The idea here is they all are crunching through incoming data. Here is the RabbitMQ architecture. We'll talk about this. Let me pause here. Deepak, do you have a question or comment?
Yes, Adityan, I have a question. So my question is, when a producer sends a message in RabbitMQ to a consumer, right? And let's say it's a direct message or it's a fan out message, whatever it is, right? When the consumer consumes that message, after that the message is not, would it be there in the queue anymore, or it would be removed?
Yeah, great point. So RabbitMQ removes the message. Kafka keeps the message for a retention period, and we'll talk about those. But yeah, you're right. RabbitMQ will remove the message, and it'll do the job of orchestrating the removal and bookkeeping of the message.
And is it even for fan out the same thing? Like if it like for fan out, I believe it would be delivering to, it's a pub sub kind of a thing, right? The multiple consumers, right?
Right.
On the same topic. So once those consumers have received the message, it is removed again, right? In fan out case.
Yes, exactly. So once you get an acknowledgement that a message is delivered successfully and the consumer has acknowledged receipt of the message, then it's ready to be removed.
And if the consumer is not there, it will still be removed?
Yeah, great point. So it potentially will be buffered until it is kind of delivered successfully and you hear back from the consumer that it's been successfully delivered. We can talk about these nuances in the next slide, but those are some things a smart broker does. You're bringing up good points. So a smart broker is exactly what this is. It does many more things. It routes messages, bookkeeping of message, life cycle of the message. It will do all those things. I see some more questions coming up. Maybe we can pause here to take questions, or we can actually talk about some details and maybe it'll answer some of those questions. Go ahead, Pradeep.
So, quick question, and I'm not from the database or anything. I'm the network and security engineer. So, quick question. So, like you give the example of when we're filling the some form online, we do auto complete on those things, right? So, in that case, it is like continuous. You will have the subscriber, right? So it will keep the message in the queue always, because it is like ongoing, right? It's a kind of continuous consumption. So how that handled?
Yeah, great point. So you're right. There will be some kind of always on subscriber that's always reading some data and informing your autocomplete through whatever it knows so far. And your producer might be the user clicking and typing keywords, things like that. Those are data that is being produced, and we'll go through some broker, RabbitMQ or Kafka or something like that, and you'll have auto-populate suggestions showing up as well. Great questions. Okay, 2 more questions, and then we can talk through this architecture. Rishikesh?
Oh, I had my hand raised from before, so I can lower it. Sorry.
Okay, sounds good. Divakar? I think you're on mute, Divakar.
Oh, no, sorry, I don't have any questions. I think somehow it was raised by mistake.
Okay, sounds good. Okay, so this is the architecture of RabbitMQ. Essentially, your producer produces messages and sends it to what's called an exchange. Exchange is a logical construct in RabbitMQ. The broker is the universe of things. It comprises of many things like exchange and queues. Exchanges are kind of entities that route messages in some ways for routing. Their job is to not do much more than that. They exist to kind of send the message to a destination. In this case, the destination is actually called a queue in RabbitMQ, and the queue is subscribed to by consumers. So a direct exchange is meant for one-to-one communication. A topic exchange is meant for one-to-many communication, and fan out is one-to-all communication. So let's take quick examples for these. A direct exchange would be the message is intended to go to one queue. The queue uses something called binding key to bind to an exchange. It basically establishes a contract between the queue and the exchange, and the direct exchange knows that there's one queue on the other end. So when it receives the message, it forwards it to the queue. The queue will keep the message, and perhaps there is a consumer on the other end of the queue. And once the message, if the consumer is alive, it will attempt to send the message. RabbitMQ, this we'll talk about more, but it's a push-based model instead of a pull-based model. We can talk about why that might be the case, but what happens is the queue attempts to push the message. Consumer either gets it. If the consumer gets it, it sends back an acknowledgement, and message is confirmed delivery, and the message can get deleted post that. Think about why RabbitMQ might be a push model versus a pull model. Any thoughts on what is a better choice for if your goal is to construct something that is very, very low latency message delivery, which one would you choose?
Push.
Great point. So there are issues with, so RabbitMQ allows you to do pull model as well. Not to say this is not allowed, but they strongly prefer you use push model. And that's the default model. So with push model, the reason a message could be delivered faster is because the moment the message arrives here, it is ready to be transmitted to the consumer. In the other case of a pull model, what happens is the consumer, when it's alive and when it decides to ask for the message, it will ask the queue, give me the message. So if the goal is to deliver the message as quickly as possible to the consumer, push model might help you with those, reducing that delivery time. Having said that, coming back to the topic on exchanges, topic exchange and fan out exchange. So fan out is easy to understand. One-to-all communication. Examples are group chats, for example. You want one message, one producer sending a message to one exchange, and that exchange is subscribed to by many queues. Perhaps you have WhatsApp or Facebook Messenger like a group chat. You have geographically distributed queues for some reason. Maybe you can have something in Europe, UK, Asia, and whatnot. So your message is broadcasted to all those queues, and then you may have many consumers, which are end entities, maybe your mobile applications that receive messages from those queues. And likewise, lifecycle management of the message is taken care of by the RabbitMQ broker. Topic exchange is a bit more nuanced. What happens is the message can have one or two fields, like the message has header, payload, and perhaps some more fields. One of those fields can act as a routing key. When you use such a setup is, let's say you know that the message is specialized, like you want to send the message to certain queues and not others. So you employ a routing pattern, which is a regular expression. So your message arrives, if it's intended to go to European domain versus US domain, let's say there's a routing pattern on domain, you will forward that message to a queue that's meant to handle messages for European domain. When can this be a good example? Think about it as let's say you have a global e-commerce website. You take orders from all over the world, and what you want to do is you get orders in some central place, and then what you want to do is decide where the order is coming from. If it's a US order, you will do many US specific things, like if US credit card processors will be contacted, then US shipping partners like UPS will be sent your order for shipment, and so on. If your order is European order, you want to perhaps make sure you're GDPR compliant and all those things. So you'll do some things related to that. You'll have a EU shipping partner, and so on. So the point is, how would you implement such a setup? You would implement it using a topic exchange, where your order data would have some field or some information on how to route the order. Your RabbitMQ setup will route your orders to queues that are specific to the task you want to do. And then on the other end of the queues, you will have services like these. In this case, who are your consumers? Your consumers are a payment service, which is US credit card processor, a shipping service, which will be contacting UPS, USPS, and all those things, and so on. So that's an example of when you might use a topic exchange. Having said that, let's talk a little more on few characteristics of RabbitMQ and when it becomes a good choice. I see a question on the chat. Why is push versus pull? What's the difference? So push versus pull model of message delivery. So how I think of it is, push is good for makes best attempt at delivery quickly. What does it mean? So if you design a message broker with the push philosophy, what you're trying to do is you're making your best attempt as the message broker to deliver the message as fast as you can to the client. Because there is no waiting time. You know when the message has arrived and you can immediately send it out to the client. Pull leaves responsibility of the fetching the message to the client. So what if the client is slacking off or delayed a little bit? What if the client is dead? Then when it comes back up, maybe there's a boot up time. It takes a minute to 2 minutes to actually request new messages. So effectively what has happened is your message hasn't been delivered as fast as it could have been if you followed the push model. Neither model is good or bad. There are just pros and cons. Push model might be more useful in cases where you want the message delivered as fast as possible. Pull model is when you don't have that high strict SLA or that much of a responsibility or something like that. Pull model is something you'll see followed in Kafka. Push model is what you'll see followed in RabbitMQ. But it's a design choice based on behaviors you want out of your message queue. Okay, few other things. Let's talk about priority ordering messages. So we talked about this, right? It's possible to do a setup where first in, first out is not guaranteed. Maybe you don't want first in, first out. Maybe you see messages coming in. Your producer is sending messages. Your consumer will read messages. But you want your consumers to read messages in a different order and not first in, first out. How would you do such a setup? Just high level thoughts. We don't have to go designing this stuff, but any ideas on how will you think about doing priority based message delivery? Yes, Rishikesh.
We will basically assign a weight or like a predefined number to the message, right? Based on what is the priority of the message. So, for example, as in your example, you said like if this message is intended for AT&T, it will probably be like a severity 1 message or something like that. And then if it is a if it is a sprint message, right, like then we'll assign a severity 2 or 3 based on what is the severity of the or the weight of the message, and then based on that we will align or assign positions to each of these messages based on their priority. So priority 1 message will be first, and then once we finish with all the priority 1 messages, right, we can then assign put the priority 2 messages in the queue. If we encounter a new priority 1 message in the queue, we will assign put it between the last priority 1 and then the first priority 2 message.
Okay. So in some ways you will reshuffle, insert in between and things like that.
Yes, exactly.
Okay, that's one way to do those things. Any other ideas, Deepak?
You can use a heap or priority queue. So for example, in log messages, right, if you want to act on the error message ASAP, right, so you would prioritize error message over other category message.
Error versus info versus debug. Okay, that's also a great example. Great. Syed, do you have something to share? Am I saying your name correctly?
Yes, thank you. So I was just trying to come up something different, and I was thinking if our categories are limited, for example, we have different, for example, regions, US, or in your example, for example, different phone carriers, and one of them has the priority. Maybe we can have different sub queues. And for example, I have Q1 and I have Q2, and my priority is always Q1. I go to Q2 only if Q1 is empty.
Okay. Sub queues with different priorities. That's also a great idea.
Thank you.
Great. So yeah, we have different ideas. The point of this was whichever way you want to implement priority ordering, it's a feature you might have use cases for. I believe RabbitMQ does it using something like a heap. Think maybe there are certain considerations, but how would that work out? Maybe you have a queue, you have a fixed length, you wait for it to fill up. This can be one approach. So you wait for it to fill up. Until it's filled up, you don't really heapify or something. But once it fills up, what you do is you issue a heapify operation, which is what a max heap or min heap supports. Of course, you have priority defined in the message. So someone assign a weight. That weight is available to you within the message. Either it's a field or you can compute it off one or two fields, but there's a way to get to the weight. You heapify using that weight. So when you do the heapify, this queue now transforms into the weighted by importance. So let's say M3 is most important, M4, then M1, M2, and M5. So it transforms into something which honors the weights, and then your messages are ready to be shipped out. This is one way. It potentially does away with edge scenarios like inserting in between and so on, but it also means there are cons, like what if a competing message has arrived, you have to break ties and so on. But you have to pick a scheme you want to do, and RabbitMQ perhaps does it this way, and the consequence of this is the fixed length queue size. So that's what I was trying to get to. It's good in these scenarios where priority based message delivery is important, and RabbitMQ will enable it. The con is it will kind of have some notion of a fixed queue length when you do priority based message delivery, because it has to decide when is the right time for it to reshuffle messages, and perhaps you can keep it configurable, but there is some notion of a queue length at that point in time. That's just one of the things. What else did we miss? And I can stop for some more questions. So bookkeeping, let's just justify this. Smart broker, dumb client. What all kind of goes into a smart broker? A smart broker does routing, bookkeeping of messages, deletion, life cycle management of messages, life cycle management, complex routing as well, priority based routing, complex routing, all those things. So what it means to have a smart broker is brokers obviously doing the major responsibilities, which is transferring the messages, but in addition to doing that, it is doing bookkeeping of the message. So bookkeeping will be like keeping track of acknowledgements from the client. Did the message reach the client or not? You can have negative acknowledgements as well. RabbitMQ allows you negative acknowledgements. What it means is client received the data, client couldn't process it. So client tells RabbitMQ that this data is bad, or it says some negative acknowledgement is possible. So RabbitMQ has to decide to maybe re-queue it and things like that. It can do multiple things. But the point is the heavy lifting of doing all that bookkeeping lies with the broker. That makes it a smart broker. Lifecycle management of the messages, deletion of the message, keeping messages buffered until they are delivered, and kind of everything from the message inception to destroying the message is handled by the broker. Dumb client just means the client doesn't do the heavy lifting, doesn't do heavy responsibilities. It only focuses on processing messages, receiving message and processing messages. It is not concerned that did you delete the message. It's not concerned with all those things. It's only concerned with receiving the message and taking care of what it needs to do. Okay, let me pause here. Pradeep.
Yeah, sorry, I have one quick question. So after the class, you will share this complete all slides, everything, right, with your notes?
Yes.
Okay, thank
you. Okay, Kaviraj.
So you mentioned about the fixed length queue, right? In the previous slide. So this a queue length, what I'm understanding is like, maybe a queue can hold 1,000 or 10,000 messages at a given instant, is it?
Yes, so not to say it can't hold more messages. What I mean to say is once it reaches that length, RabbitMQ may decide to reshuffle the queue to do the priority based ordering of messages and then ship out those messages. It will probably still keep receiving more messages, but it has to decide when is the right time for me to reorder the messages. So you may have some configurable length allowed that help you reorder the message.
Okay. So basically, you're saying that once the fixed length is reached, that is when you are actually doing the reshuffling of these and messages and keep it in the priority order, is it?
Right, exactly.
Okay. So my another doubt is in that case, right? If we are having a continuous flow of low priority and high priority messages coming, right? And you have this low priority messages keep accumulating in the queue, right? So what is our strategy so that we will deliver the low priority message as well, because we are otherwise it's kind of you are not delivering the low priority message in a continuous flow of low priority and high priority messages coming to the system, right? So how do we design that case, right? Do we need to increase some processing power of the client side machines or some? So what are the strategies we should use to make sure that even the low priority messages are taken care?
Yeah,
needs to be corrected in the client side, right?
What I would hope for is you have some form of like high priority message first, then high and medium and low priority, and RabbitMQ will attempt to deliver these messages as well. Once these messages have been sent out, it will try to send the low priority messages as well. But you are bringing up a good point. There are situations where the client got the message. Client tells RabbitMQ message doesn't look good. Can you reprocess it? So there is a notion of you can send the message back into the queue, re-queue it, and that can bring up some interesting edge cases. Like a message goes back into the queue, client gets it, client says, no, I don't like the message. It goes back into the queue and it kind of loops around and goes into an infinite cycle of just doing that. And such scenarios.
I think in that case, like normally we will have a error queue or something after like in a certain number of. But my concern is like if the number of requests coming to the system or the flow or the rate is really high with the high priority messages, than the push, right? How it is pushing the messages to its clients, right? And client needs to be acknowledged to remove these messages from the queue, right? So if the client is a bit slow, then basically your low priority messages may never send to your clients, because you are always keep getting the high priority message. That is the rate you are actually pushing into your downstream clients. So I'm just thinking, so we should have some kind of uh, numbers, like your client should be taking care of messages in this rate if your input is coming in this particular rate, something like that, right? So that also needs to be considered, these kind of systems, right? Because there should not be any bottleneck, or you never deliver this low priority message or something like that should not happen, right?
Great point. Great point. We will talk about this as well in the Kafka part, but you're bringing up a good point. So ideally, we would like the rate of pushing messages to be roughly somewhere less or equal to rate of consumption, so that you're not bottling up messages. If you see messages being buffered and not delivered, there are many scenarios that can happen, and you can either increase number of consumers, so you can start to deplete messages faster, or consumers can actually push back. There's something called back pressure.
Right.
So consumer will tell the queue that you are overwhelming me with the number of messages. Can you slow down? The queue will tell the producer that you slow down producing the messages. So that's what back pressure is. We'll talk about this in the Kafka part, but those are different strategies to deal with what to do if rate of production of messages is faster than you can consume and so on.
Yeah, I think even the number of items in the queue, that also use as a measure to scale the system, auto scaling part of this cloud infrastructure, right?
Yep, exactly. Great points.
Okay. Thank you.
Any other questions? Maybe we don't want to delve a lot on RabbitMQ, but just wanted to highlight design choices here. We should probably shift to talking about Kafka next, so that then we can.
Adityan, if I may comment, so is this in the smart broker dumb client? Is this the reason why RabbitMQ is supposedly not able to scale? For the large distributed systems, right? Is this the reason? Because they are smart brokers, and smart brokers put an artificial top limit in terms of scalability.
Great point. Yes, that's one of the reasons. The other reason is also that think about it this way. So RabbitMQ's SLA is actually message delivery will be faster than Kafka. As we'll see, Kafka will deliver messages in second level latency, or maybe perhaps millisecond as well. But RabbitMQ will deliver messages faster. But in reality, for real-time systems, the question to ask is few seconds too late? For most scenarios, it is not too late. For most scenarios, few seconds is perfectly reasonable. And that kind of plays into Kafka's strength. So Kafka is built to kind of scale to billions of messages. And the trade-off is you're delivering messages at a second level latency, but that is perfectly reasonable for extremely large volume of data. RabbitMQ's scalability is limited to not that high volume of data. You can keep adding more infrastructure, more nodes to your RabbitMQ and make it scale, but it's not meant to scale as large as Kafka. So that's one of the reasons why disk style queues like Kafka have become more popular. RabbitMQ is useful for use cases where you want to beat Kafka's latency times in terms of delivery, and where millisecond level latency delivery is very, very crucial and things like that as well.
Yeah, thank you. Makes sense.
Okay, great question. So we have the next section on deep dive into Kafka architecture. Before that, maybe it's time for a short break. So we can take a 10-minute break. And what we'll do next is we'll study disk style queues like Kafka and dive deep into Kafka similarly like RabbitMQ. And then we'll go back to solving our interview question for the remainder of the time. It's 11 a.m. Why don't we take a break and back at 11:10 a.m. PST? See you all in 10 minutes. Hello, everyone. Can you raise hand or something? Okay. Sounds good. Let's continue. The next section is talking about Kafka. Any questions so far? Okay.
Just one
yeah.
question, because I'm from the network security background and I'm in this IT trade for the AWS architecture. I'm trying to correlate it, how this will applicable to me.
I see. How will this be applicable to you? One
as an AWS architect and with a network and security specialization.
I see. One way I can see it, of course, if you encounter system design interviews where they want to quiz you on real-time streaming related.
But does it really, do they really go into system design for the AWS architect kind of role?
So you may be required to generally, I know perhaps it's a broad role, but I guess you may be required to know how various AWS technologies work and perhaps other products, design principles you can use for certain use cases, but you may be generally required to know a broad range of things. But having said that, you may also be quizzed on how does something work underneath and like some technical deep dive as well. And that's when some of this can be useful. We can always refer to AWS related technologies as well. Like Kafka is also offered by AWS. They offer Kafka managed Kafka offering, but it's good to know how those technologies work underneath.
That's for the knowledge purpose. I understand that, but I'm not expecting them to go in that depth for the AWS architect. Okay, design Kafka like system or the RabbitMQ like system.
So system design interview could be breadth or depth wise. If you encounter breadth level system design, you may not deep dive as much as we will do in this class. But if you encounter some depth level questions, then this kind of knowledge will help at that point.
Okay.
Okay, great question. So next section is on studying disk style queues, Kafka being our main topic of interest. But this slide is here just to kind of reinforce that Kafka is also not the only offering that does streaming. Kafka has many competitors like Splink, Storm, and Spark Streaming, and things like that. They all have different origins and different design decisions. Studying all of those in detail is potentially a very long endeavor. So we will contain ourselves to learning about Kafka. I have some experience in Kafka and Spark streaming, so we can talk about those as we discuss in this class. But mainly what we want to know is how it differs from RabbitMQ. So Kafka, just taking a step back, AWS offers MSK, Managed Service Kafka or something. That's a managed offering. There are companies like Confluent who build managed Kafka. The point is, Kafka is open source. You can choose to deploy it yourself in your infrastructure and have teams manage it for you, or you can ship the responsibilities of managing a Kafka cluster out of your company and buy a managed offering. Both Kafka and RabbitMQ are used. As you can see, cloud providers ship them as managed services. Kafka is very good for extremely high amount of scale of data. So it's scalable, fault tolerant, it's distributed and partitioned. So we'll talk about all these things, how Kafka achieves what it does and is a vital component of a big data scale system. So Kafka has the notion of brokers, broker replication, topics, and partitions. commit log and consumers on Zookeeper. Let's talk about this one at a time, and we can build up our intuition. So like with every message broker, there is a producer and consumer. Producers are external to Kafka. These are your agents or apps or code. All of those can be producers. The producer itself can produce human generated data or system generated data. It's a vital distinction, but you can have various kinds of producers is the conclusion. Human generated data is an example is you scrolling through Instagram is human generated data. Your actions are generating the data that eventually goes into some Kafka in Instagram architecture, and your data is studied and recommendations are generated and so on. System generated data is what Datadog does, for example. The question for today's class. Nobody is actually generating the data except it's the system logging its own metrics. Regardless, all that data goes through your producers and comes into the Kafka ecosystem. Kafka ecosystem has a notion of a topic, which is, you can think of it as set of similar data or a stream of similar data. Similar can be some business definition of similar. So let me give you a concrete example of what a topic could look like. Click events is a topic. This is actually true in many companies. They can have a topic in Kafka for recording all the clicks that happen in your social media web page. This topic will have a stream of clicks available, and it will be a billions of clicks if you think about it. Instagram scale will be billions and billions of clicks. You can have topics like view events, views, scrolls, all that stuff. If one, and what needs to be kept in mind is a topic is a logical construct. A topic spans multiple machines, spans multiple nodes. It is not residing on one node. So a topic is broken into what's called a partition. So the hierarchy is topics broken into partitions, and partitions are broken into segments. Let's talk about what partitions are and what segments are. So how does a click event topic look like? So clicks are coming in. You have some Kafka topic for housing the click events. Now imagine there are 100 million clicks coming in. It's not feasible to store this in one node. So what do? You break the data down into multiple chunks of data. That chunks of data is partitions. So let's say you have 10 partitions, P1 through P10. What it means now is, if you partition your data roughly equally, then every partition would have roughly 1/10 of your data. 1/10 of data, which would be 10 million clicks in each. This is if the partitioning scheme or whatever you use is able to kind of split your data roughly equally. Now, why would you do such a thing? Is because to handle such a big scale of data, you have to be able to handle it across multiple nodes. Partitions in general map to physical nodes. Partitions usually map to physical nodes. Why is that the case? Let's say you have one node 1. For topic clicks, it doesn't make sense to have partition 1 and partition 2 residing on the same node. You could if you wanted to, But if you do it that way, what happens is if the node goes down, you've lost 2 partitions of data. The point of partitions is to give you a scalability construct as well as a fault tolerance construct. So you don't want to house partitions, co-locate 2 different partitions on the same node generally. So each partition may reside on a different physical machine altogether. Partitions have replicas. Replicas are copies of data. So what does a true setup look like? In one node in Kafka could actually have partition 1 for some replica, partition 2 replica 1, and so on. Basically, what I'm trying to say is partition 1, let's say there are 3 replicas, 3 replication factor. What it means is, in addition to your data being partitioned, every partition of your data will have a copy of data, 2 more copies of data. So in total, 3 copies of data will live. And again, likewise with fault tolerance, you want the replicas to live in separate nodes, because 2 replicas living on the same node is no good use. So when the replicas live in different nodes, you can have such a setup where a node actually has 2 partitions, 2 different partitions for perhaps 2 different topics and so on. Their replicas can be co-located because they are completely different data set altogether. So the point is, partitions are something you configure. You can kind of calculate, estimate how much data is going to be stored and needed, and how much memory disk space each node has, and you can kind of inform the choice of partitions. You can grow the number of partitions over time as your data grows, and so on as well. Segments. So let's come to segments and talk. We can briefly talk about this. What is it and why is it needed? So one thing to note it is Kafka has the concept of retention policy, which means your data lives for a time period configured by you in the retention policy. So if you say 3 days to 14 days, what it means is even if your data is read by a consumer, it's not deleted. It is going to stay there for a duration of time specified by retention policy. So let's look at an example of how this can work in terms of cleaning up your messages. Let's say you have so much data coming in that you have Jan 1 clicks happened, Jan 2 clicks happened on Instagram and so on, and Jan 31 of 22, December 31 of 22 has arrived. Jan 1 of 23 arrives. You want to kind of clean up, if you have 1 year retention window, how will you clean up all the Jan 1 messages? Will you go and scan through all the billions of messages to drop what you need, or what are some ideas on how to efficiently clean up messages once messages go outside the retention window? Yes, Kaviraj.
Maybe we can have a TTL for these messages.
Okay, some form of TTL. Any other ideas?
Maybe we group them as we archive them.
Group and archive. Okay. Deepak, did you also have something to say?
Yeah, I don't know whether it does this or not, but using something like a ring buffer or something, right?
Mm-hmm.
That kind of policy. But
okay,
I'm not
sure
how it is implemented. Because there could be different policies for different topics and stuff like that, right? Retention policies.
Yeah. So what we want to keep in mind is messages are stored on disk. Everything is stored on disk in Kafka, which means disk IO is slow, slower than memory, but not so slow that it's not useful for our needs, which is one reason why RabbitMQ's message delivery is faster than Kafka, because memory IO is faster than disk IO. So memory style queues will deliver messages faster. Having said that, disk IO style queues are good for kind of large scale storage and processing of data. And one way Kafka does such a cleanup is it will eventually store everything as files on disk. So those files are called segments. And the point is they will be time partitioned files. So in
Your
this
daily segments, right?
Yeah, exactly. You have daily segments of data. So you'll have a group of files for Jan 1, you'll have a group of files for December 31, and so on. And when Jan 1 23 has arrived, what happens is Kafka knows that these files need to be dropped. So it will mark them for deletion. Mark for deletion. It doesn't need to scan through anything. And marking for deletion just means it's even more performant than actually deleting the file. So make them unavailable to be queried anymore. Then at some cadence, some point in time, some background job will sweep through everything that is marked for deletion and actually recover the space. So then delete and recover space. So that will eventually happen at some point in time. But the first thing that will happen is it will get marked for deletion. So this construct of segments is what allows you to honor Kafka's retention policy and helps you kind of scale to big data needs. Yes, Pradeep?
Marking happen at the end of the retention period, or it happens at the time of storage, because he already know when it's going to delete this file. So it can mark in advance that, okay, comes January 1st, 23, this segment is going to delete. So marking happen at the time of writing itself.
That's smart. Yeah. That's
so marking happen when it storing the data, or marking happen when the time expire?
That's a great question. I don't know for a fact how exactly that will be implemented in the lower level details, but that's a clever idea that you can mark it already with a future timestamp on which it will get deleted. Some form of TTL itself. I would imagine that would be the optimization they apply. It seems less performant to actually mark it for deletion later. Great idea. Any other thoughts, comments, Kaviraj?
So we understand these segments. Each segments will have a TTL. That is what you mean to say, and there is another program which will do the cleanup.
Correct. Yes. So each segment will have a time when it will expire, and then there will be a background job that will clean up the actual files on disk and recover the space. And these segments are configurable. So in this case, it's day level segments, but you can have minute level, hour level segments as well, depending on what your retention policy is. So if your retention policy is 3 days, perhaps you want minute level segments on 3 days. So you can have a fine grained control on minute by minute expiry of data and so on.
Okay, so that means if I have a 3 days of retention, so every 3 days there will be one time this cleanup activity happens, right? No, actually, I mean that in that case also it should be every day there should be a cleanup happening, right? Because you will have always 3 days of data. Like on the 4th day, you will clean up the very first days of data, and 5th day you will clean up second day of data. All right. So it could be like a day or less. I mean to say you can even say that 2 times. I mean, I'm just thinking like there is no point of cleaning 2 times if you have a 3 days of retention period, like, because in the fourth day you have to really remove the entire first days of data, right? You don't need to run 2 times the same job, right? I'm not understanding, like,
So it's
why.
configurable is how I would look at it. It comes down
Okay.
to you couldn't clean up more than once in a day. That way you will always keep it a rolling window of 3 days. Like time is continuous. So you can
So
have
then, if I'm doing more than once, like, then what is going to be my filter criteria? Because all these files will have a date timestamp. I think I'm just thinking that way. So, I will, that's what I am assuming is that, that particular job fetch all those files with, like, which is 4 days old, and try to delete it, right? So if you want to run it in 2 times, then you may have to keep it in the keep the or check the minute level also, like, okay, the very first 12 hours data I'll clean it on this time,
yeah.
to 12. Yeah. Okay.
Exactly. Yeah. So you can have lesser granularity of time. Like you can have minute level segments, first minute, second minute, third minute, and so on. And then
Okay.
you can decide how many to clean. Or you can have hour level segments for hour 1, second hour, and so on as well. So those can be done. Depends on how you want to configure your, how often to clean up and things like that. Those are considerations. If you don't want to clean up that often, you can potentially have a larger segment like day level. And if you want to keep it even more fine grained, because you will pay for storage of data, that's important to remember. Like as much data is not cleaned, that extra data is also getting stored, and usually you pay for storage and compute of the data on these resources. So it's a business decision and kind of cost and effort decision at the end of the day. But the point is segments enable you to do efficient cleanup. That's what I wanted to convey here.
Okay.
Great discussion.
Thanks.
So coming back, so we have partitions. Partitions have replicas. You configure how many replicas. Replicas give you fault tolerance. We didn't really talk about Zookeeper. So here's one more thing. Zookeeper is a separate service, manager service, if you will. Zookeeper is a service that can hook up into many kinds of infrastructure. Kafka is just one example. You use Zookeeper in many other products or technologies that you interact with. The point of Zookeeper is it's a manager service, meaning it stores metadata. Metadata like which hosts are alive, which hosts are dead. It will store like new topic. If you create a new topic in Kafka, new topic registration, and those things are handled by Zookeeper. Leader election is also something Zookeeper can do. What does it mean to do a leader election? So look at it this way. Every partition will have replicas. So topic clicks is, we have a clicks topic which has 10 partitions, and one partition has 3 replicas. So how does this actually look like? You have partition 1, replica 1, partition 1, replica 2, partition 1, replica 3. Now, who decides which partition is the leader and which partitions are the follower? How it might work is, if this is the leader, the others might be the followers. What does it mean to be a leader? So all the writes go to the leader, and reads can also come off the leader. while the replicas are there as stand-up mechanism to they're standing there in case the leader goes down. One of these two gets elected as the leader, elected or promoted to be the leader, and it can start serving the reads and writes. So writes are effectively your producer is writing to your replica one or primary leader one of your partition. Your leader will propagate all those data changes to your followers, which are other replicas. Perhaps you can have reads configured of other replicas to reduce load on one of your instances. That's possible. You can send reads out of other reader replicas, and you can have the primary one be the entity that takes in writes. Whichever way you configure your system, the point is these things are built for fault tolerance. So what I was coming back to is who does the job of promotion or election of leader. This is handled by Zookeeper, kind of a neutral third party of some ways. So you will have some external consensus. Zookeeper will orchestrate your consensus and agree who is going to be the leader after leader one is dead or something like that. Those are.
Sorry to interrupt you, but one question. So this leader and follower, these are all like you can define this as a parameters when you set up this system, or like the system, like the Zookeeper itself decides who will be the leader and stuff like that.
Yeah, you can set it up while you're setting up Kafka. You get to decide that. So you get to decide how many replicas you want, and you can potentially instantiate one of those nodes as the leader itself. So you can do those things once you set it up, and then Kafka will take care of continuing to maintain some leader and some followers going forward.
Okay, cool.
Deepak, do you have a question? Comment?
Yeah, Adityan, one question I have is, they also have Kafka with Kubernetes, right? So in that case, do you still have Zookeeper, or Kubernetes take the does the responsibility of Zookeeper?
Kafka with Kubernetes, interesting. Is that like each node is within a Kubernetes pod and things like that, or?
I think the whole cluster is managed by Kubernetes, right?
Oh,
but anyway, we don't need to if you are not aware of.
Yeah, I haven't encountered that.
Yeah.
But,
Another question I have, right? So as a producer or a consumer, right, on a given topic, when you're publishing a message, right, do you need to know which partition it needs to go, or the broker figures that out automatically for you?
Yeah, great point. So you're coming to anatomy of a write operation. How does a write operation work? Maybe it's a good time to just talk about it. So from the point of a producer, what happens? Producer wants to write to Kafka topic. Producer should know which topic to write and which partition to write. Now, who tells you obviously know which topic to write because you are deciding, like you want to write clicks. So you will tell the producer, I want to write clicks to clicks topic. Partition information is the leader partition. Who tells it? When producer wants to write to Kafka, the API will contact Kafka. Kafka will have Zookeeper as well. Zookeeper will tell your producer that for this topic T1, there are 3 partitions and 3 replicas. 3 partitions and 3 replicas. Out of that, here is the leader. It will tell you which leader, and then the producer will learn the leader's information, perhaps its IP address or host name or whatever, and then send the write directly to that leader. So the actual write reaches the leader of the partition you are trying to write to, and then the write gets propagated to the followers. That's how the anatomy of the write operation happens. Read operation, anatomy of a read operation is the other way. So the consumer, Kafka is a pull-based model. So consumer will pull data out of Kafka. Kafka won't push data to the consumer. So when the consumer wants to request data, what it does is, from the consumer point of view, you again have consumer. What do you need to know to read data? You need to know which topic you want to read. So you tell the consumer, I want to read clicks. Again, clicks, consumer will open a channel, open line of communication to Kafka. Kafka broker and zookeeper will tell the consumer that for this topic, you have 3 partitions and 3 replicas per partition. And the read you want to go to is, you send your read to this IP address, which will be one of the followers, or it will be a node that is chosen by zookeeper to send the reads to, and the reads will go to that node. If that node is unavailable, there's potentially a backup node available for you to read from. But effectively, the consumer will get told that send your read request to this specific node, so that read goes to exactly that node. That topic T1 and partition will receive the read, and then it will poll the data and fetch the data, get a stream of data that consumer can work on. That's the anatomy of a read and write operation.
So in this case, does this determination or resolution of which partition to write to and which partition to read from, is that done by the Kafka client-side producer consumer libraries automatically, or does the user, the end user, the end programmer of consumer and producer would have to do it manually, like, by himself?
Yeah, this is a great point. So I think both possibilities are allowed. If you know the partitioning scheme, like if you know where the write should go to, so for each message, it will get hashed. And then if there are three partitions, the point of a partitioning scheme is it will tell which partition should that data go to, first, second, or third. If you know from the point of producer how to hash the data and which partition it should eventually go to, you can directly kind of set up writing to the partition. If you don't know that, Kafka will tell you which partition it should go to, and then it will orchestrate the library will still send the write to the relevant partition.
I'm still a little bit lost, Adityan, here. Let's say a producer is producing on one single topic messages in a round robin manner, right? So let's say message 1 goes to partition 1, message 2 goes to partition 2, message 3 goes to partition 3, right? And message 4 again goes to partition 1, and so on and so forth, right? On the consumer side, how does it know what partition to go to so that it can get the message in correct sequence?
So one thing to notice, message ordering is guaranteed within a partition. There's no notion of message or ordering guarantee across partition. So when you read from a consumer, you're generally reading from a partition alone, because that will guarantee ordering of messages. You can read from multiple partitions, but then you will not get the stream of messages you read from both partitions will no longer have ordering guarantees in it.
So how do they get this time series data, construct this time series data? Because then in that case, they have to write sequentially, like to write to partition 1, and then when partition 1 is full, then write to partition 2. Is that how it happens, or?
Yeah, great questions. I think we will talk about these through the interview example as well. But in general, what happens is, for each consumer or a group of consumers, consumer group, generally you want to read from one partition. And then to read from other partitions, you'll have similar consumers and consumer groups that will read from partition 2 and partition 3 and so on. So by nature, you're reading ordered data, when you read from each partition, will have ordering guarantees, and you can kind of construct your stream here again. You may, if you want to figure out ordering across partitions, you may have to pass some timestamp field and so on and compute ordering across partitions. But Kafka will make sure message arrival and ordering is guaranteed within each partition. There is no notion of ordering across partitions because of just how the infrastructure is set up. But we can dive in more on this topic again in our interview question.
Okay, thank you. Yeah, I think this helps.
Okay, let me go to some folks who haven't discussed that much. Animesh, do you have a question?
Yeah, I was just confused. Like when the consumer is reading, they're not reading from a partition, isn't it? They're reading based on a topic, and partition is the hidden logic that I'm guessing Kafka is maintaining. Because I was listening to what Deepak was saying, when a producer is writing the data, they're writing on a topic, they're not writing on a given partition. That's what my understanding is. And the topic gets hashed into a partition based on whatever the setup is done. Is that right? Or is there like, am I missing something?
So you're right that the topic is, there's a hashing logic to partitioning the data, but
Yes.
the write from the producer side actually goes to the exact partition where that write should have been. It doesn't go to some, think about it.
Or it doesn't go through Kafka, like just like load balancer, isn't it? Like we were thinking about it, like it would go to the Kafka based on the topic. They would do the hashing because client cannot maintain the hashing logic, I'm guessing.
So one way to think of it is when the write operation begins, it contacts Kafka. Kafka's broker and zookeeper will tell that library that you send this write to this location.
Okay. So initial handshake will be based on the topic, I'm guessing, and they will, based on the topic, they will say which partition to go to.
Exactly. Yes.
Okay. And there won't be any round robin, because I remember Deepak was saying something about round robin. Round robin is not happening when you're doing a write. The write is going to a given partition based on the topic. And the topic is a partition is figured out while you're doing an initial handshake to say, I'm going to start writing on this topic.
In some ways, for such a scenario, you will end up being a round robin scheme, because when each write will get told to go to, it might be a very simplistic example. This got a write, partition 0 got a write. Then Kafka will tell the next write that since this is already on, you go to partition 1. Then it'll tell go to partition 2. So each time a new write is issued, it may actually just become round robin by default. And Kafka will be keeping track of where the writes are going and distribute the writes in a round robin fashion.
Okay, then I'm confused. Like, how would a consumer read the data from, and how do you maintain the, if you have to maintain some FIFO or some other logic to say you need to consume the data based on the maybe the time, like the time when they were created.
Yeah.
Is there a way you could, because I'm guessing just 0, 1, and 2 that you mentioned, they are not the replicated data. They are actually a partition, and the replication is just hidden from us.
Yes. So
0, 1, and 2 are the separate partition, isn't it?
Yeah, these are partitions.
Okay, individual partition, not the replication, like 3 ways replication that we typically do for fault tolerance and other stuff.
Yeah.
Okay, so that's what I was thinking. Like, so when you're getting the data, how will you? Because you will hash it. Because I was thinking it should be a consistent hashing, isn't it? Like to say, this topic, if you're thinking about reading this, always go to this particular, go always to this partition.
So one thing to keep in mind that we didn't really discuss is, in the case of event-driven systems, there are lesser use cases where you want to. What I mean to say is, your goal is to consume as much data and can act on those results. It may not be critical to actually even get the ordering of data right. Think about click or something. clicks, views. There's a notion of idempotence. Maybe I can just talk this now, which is the same data, the same actions taken on the same set of data will result in the same output. For most cases, like machine learning models or any big data system, we don't focus as much on ordering of data or guarantees of data, but more like consume the data and there will be similar outputs coming out of the same copy of data. So we potentially don't even need that. How do we figure out ordering? There may be certain examples, certain use cases where ordering might be necessary, at which point the message that you're passing can have some timestamp field in it, and you can break that ordering guarantees using that timestamp field, or some form of logic on your consumer side will be needed. But in most cases, we don't even need such a scenario because we have big data stream and it's ordering is not of very big importance.
Okay. So are we making an assumption that this message, this Kafka stream is only used for the topic that we are dealing with? It's like the monitoring thing that we are building. It's not going to be used by some other application. This is only a single topic thing that we are discussing.
Single topic.
I'm thinking like it won't be for another, like maybe click stream thing. Right now, we're just collecting a system related matrix that we talked about in our problem statement initially. Because that's why I was thinking, like consumers will be different for the different kind of events, isn't it? Like here, all we are assuming is all the consumers are consuming this, can consume all the events. They are not looking for a specific event.
Right. In this example, yes. In our interview question, we'll see how that differs. We'll try to apply Kafka knowledge shortly, and we'll design multiple topics and things like that too.
Thank you, Adi.
Okay, great. Let me go to some more questions, but brief comment on Zookeeper. We don't need to get into a lot of it, but Zookeeper is going away in Kafka 3. Kafka 3 won't need Zookeeper. They're building things separately. Zookeeper has security issues and whatnot. So you'll see Zookeeper not being talked about in the future. But that being said, I just wanted to include it here to just complete the picture on how things look like in Kafka 2. But you won't see it in Kafka 3. As Kaviraj has already put in the Q&A, you can read more on what's happening in Kafka 3. Karthik, do you have something to add?
No. So one question is in a consumer group. In this figure, in this drawing, right, consumer group is taking from 3 partitions. But I think what I understood was one consumer group can only take it from 1 partition, or it's a topic level. I thought it's a partition level. Can you correct?
Yeah, great point. So there is no hard and fast rule. In general, yeah, it's right. The good practice might be to focus a consumer group to get from 1 partition alone and have a separate consumer group for another partition. That being said, nothing prevents you from actually reading 2 different partitions within a consumer. That can be done. And you might want to do such a thing if you want to, let's say, have ordering across the whole topic. So if you want to have some form of ordering of data and process data in some order across all 3 partitions, then you have to read all the 3 partitions, figure out ordering within your consumer, maintain ordering, and then do some action. So you may have examples like that.
Okay. And then for, I think, if we take that example, then FIFO could be easily managed, right? Because one producer is giving to only 1 partition. This consumer group, it has to be hashed to that partition, right. So that way, right, you don't have to worry about FIFO. It will already be maintained. If you want, like for example, 1 partition is for sales, 1 partition is for payment, or 1 partition is for marketing. Though the topic would be the same, but the partition is a bit different. Topic would be like a e-commerce, but inside that there are 3 different buckets of partition. the consumer group can actually take it from that partition, and we can achieve FIFO in that way. I am thinking if a consumer group is that. So, and one more thing about Zookeeper. You said it's going, but I was thinking, so should the producer, so Kafka internally will be calling Zookeeper, not the producer calls a Zookeeper and Zookeeper, because Zookeeper is responsible for leader and election node, right? So if I go to Zookeeper, Zookeeper knows which leader should I give, and it'll give it back. So shouldn't it be we contacting Zookeeper rather than calling Kafka, and Zookeeper will give us the node back, like this is the leader. I was thinking, but just so it's Kafka only we need to call, not Zookeeper to get it.
Yeah, exactly. So Kafka will be called, and Kafka will kind of have Zookeeper also into its ecosystem, and the broker will be talking to Zookeeper and retrieve the information it needs to send to the producer, and then the producer will find out where to send the write and reads and things like that.
Okay, thanks.
Great.
Hey, one question I had, if I may. So this, why do we need to have a consumer group? And then another is like having this consumer group. How does it really? I mean, wouldn't that make it tied to a certain topic always?
Yeah, great point. So why we need consumer group? Think about it this way: consumer group is generally one or more consumers doing the same work is how to think of it. Same work. So if one or more, when one consumer can't hold up with the amount of work being given to it, you want to add a second, third consumer as a unit of scale so that more work can be handled by the consumer. So that's the notion of a consumer group. So if you, let's say, one very quick example will be consumer groups. If you have one consumer group per topic, for instance, you can elastically decrease the number of consumers depending on the amount of data coming in. If data grows, you grow the consumer group and so on. So it's kind of a unit of work in some ways. And the point of having consumer group is they're doing the same work, but there's just multiple nodes that will keep up with your amount of data coming in. Consumer group.
So if you go back to your previous slide, right? Like, so in there, you know, where you had, this one. So in this, you're saying that there is one producer which is having partition 1, 2, 3, right? Which is like basically producing A, B, C, D, E, A, B, and A, right? So these will go to one consumer group, and then the consumer group will decide which of its consumer will consume all of this, right? Or is it one-to-one mapping with the partition and the consumer in the consumer group?
In the way the diagram is constructed, it's the case that this consumer is talking to P1, this consumer C2 is talking to P2, and this consumer is talking to P3. Each consumer is talking to one partition in this case. It doesn't need to be this way, but the diagram shows it this way. And then the whole consumer group will have the entire data within it. So then they can kind of do any ordering based problem solving. Like each will have orders. Order will be guaranteed within each consumer, but not across consumers. And then if you want to break ordering, you can share information based on some timestamp field and so on, and break the ordering and figure out a true ordering across partitions. Something like
that. But then the essential thing is, irrespective of number of partitions and the number of consumers in the consumer group, you will have one topic to one consumer group, correct?
One topic to one consumer group. It is possible to have multiple topics to a consumer group, and I can give you one example for that. So likewise, nothing is set in stone. It depends on how you configure it. But let's think about it this way. You have clicks, views, orders. Let's say you have a topic for clicks, view, and order, and you are constructing this funnel. somebody viewed a post on Instagram, clicked on it, it led to an Amazon page, and then someone ordered. Now you want to figure out who ordered, where did your customer come from. So you have a consumer group C1. This reads from the clicks, it reads from orders, it reads from views, it reads 3 different topics. What this consumer does is join your clicks with views, and then constructs that I sent an ad on Instagram, someone clicked on it, someone viewed it, clicked on it, and then joined that with orders. And now I know where my order came from. So you can read multiple topics from a consumer. And often the use case for such a thing is you want to join data across different topics and figure out cause and effect relationship or something similar to that. This is something that's pretty common.
Oh, okay. So basically, in this case, it's like like together all these things you are going to make one data set, and that's why they're all going to go to one consumer.
Exactly.
Okay.
Exactly. Cool. It's kind of solving a common problem as well. When you show ads on Instagram and it leads to a actual transaction, you showed an ad of your product that you're selling on Amazon, but you're marketing on Instagram. When the order happened on Amazon, how do you find out who led to that order, so that you as the customer can now pay Instagram for referring that order to you? So how will it do that funnel tracking kind of situation? That's when such things come into play. You will track the views and clicks. You'll have some unique identifier which is passed between these kind of different messages, and then you'll be able to tell one-to-one that here's a view on Instagram, it led to a click that led to an order on my Amazon listing, and now I know my clients are coming from Instagram, and so I should bump up my ad budget for Instagram and so on, things like that. So you can do such things. These are streaming joins. So they're joins of data, but on streaming data is coming in and you're joining data and figuring out what's happening.
Cool.
Okay, great discussion. Karthik?
Sorry, it was from my earlier question. Sorry, I didn't lower my.
Okay.
I'm good. Thank you.
Deepak?
Oh, I'm sorry. It was by mistake. My hand was.
Okay. How about Kaviraj? Do you have something to share?
Yeah. So I'm just thinking, like, if you really want to scale it, or horizontally scale it, right? And then you need to have multiple partitions, right?
Mm-hmm.
But at the same time, if you really want to guarantee ordering, then you cannot really have multiple partitions, and so I'm just thinking, if you are designing a system where ordering is a must, then the only way we could do is like vertical scaling, is it?
Yeah, this is a good point. Maybe not fair to say only way to do it with vertical scaling, but definitely easier approach to take. If you just have one partition, it will always be ordering is guaranteed, but then there are bottlenecks. So you can potentially have multiple partitions, but then you will ship the work of breaking ordering to the consumers. It will become a very difficult problem to solve. So in some way, it's simpler to just have one partition if you want ordering. That being said, for big data systems, it's generally not the case. We don't care about ordering as much. Like it doesn't matter clicks, views. It doesn't matter which click came in first. We want to build something that will ingest billions of clicks and produce your outputs. So we won't encounter that many examples where ordering is important.
One scenario which I could think of, like, um, some kind of file processing where the order really matters. So you read from the for example, like there are devices list or something like that, and this needs to be processed in a particular order, right? So, and you have a large list, but I'm just giving an example, but it may not be that huge, like a billion devices in the list or something like that, but
Right.
it could be thousands, right? A couple of thousands and all, right? So, but I'm just thinking, uh, if that is the scenario, um, maybe a good idea is to have a single partition for that particular topic,
I
and
think
you can have multiple.
sorry to interrupt you, but I think one way to solve this is, I mean, this is just my suggestion, and maybe you can comment on it. But wouldn't the producer itself put a certain ID or something like that, and then like an ordering ID, right, or a primary key, and then the irrespective number of partitions we have or whatever we did for in terms of scaling it, right? Whenever the consumer receives it, he'll just rearrange that order. I mean,
That's a good
But
idea.
again, but the point I think in my experience previously, what we normally does is, like the big file a we chunk these list of device records, and you will keep a shorter list, and that is what we pass to the next person, right? So that is basically the list which we are actually putting into this topic. So the consumer, if they want to keep this order, again the same, because the problem is, like the requirement it's some years back, but I'm just thinking, I'm trying to recollect it. It's like which specific record is failed, right? So you may need to mark that, okay, in this particular file, the record or the device which is in the raw of, like 5,000 or something like that, or 10,000, or that particular raw device, in that particular raw, that particular device is not a genuine device or something like that, right? So to mark that specific failed record, you need to keep the, because you are marking this in the original file, right? So you may need to keep track of it. I believe I'm not very sure about the scenario, but something similar to this. So even if you chunk this, your consumers should process it in an order, or maybe, as he mentioned, like maybe you should introduce some additional key, and later an aggregator should take care of that logic to keep again back to the order or something like that. I'm
Yeah.
just thinking that scenarios, right?
Yeah, great discussion.
Mhm.
But yeah, I think that's a pretty
Okay.
involved problem of its own. Let's
Yeah.
table that for a bit
Okay.
and continue with.
Yeah, please. Thank you.
Yeah. So one more thing to mention before we start up our interview question is notion of offsets, which we didn't talk about. So offsets are places in the queue where you've successfully read. So a consumer, when it reads C1, when it's reading from Kafka, each time it fetches messages, it will pull messages and process the message, which can be whatever action it takes on the message. It will mark its place in line with what's called an offset. So once it's done processing M1, it will say my offset is incremented to 2. Once it's done with M2, it will say my offset is 3. The point of doing this is when consumer dies, it will know its place in line, and when it comes back up, it will read the queue again from the last place it left off. So that's the notion of offsets. And offsets are, in fact, internally stored in Kafka in a topic of its own called _consumer offsets. It's a reserved topic name, but the idea is you're kind of storing where each consumer is successfully read in the Kafka queue. That's the notion of offsets. If these messages expire, then the consumer will kind of obviously, let's say by the time consumer comes up, if M3 is expired with the retention window, it should go to the next available offset with data available in it. So that's a little bit on offsets. Let's briefly recap all this stuff. We didn't really touch a lot on priority routing in Kafka, but Kafka doesn't support such a thing, as you can expect from something that's built for big data scale. So in-memory style of queues like RabbitMQ are good for very low latency delivery of messages. Kafka is disk style, so built for scale of data. Second level latency is not too slow, is the thought process we're going with. Kafka is a dumb broker smart consumer model. Why? Because think of it this way: consumer pulls the data, consumer keeps track of its state in offsets, and consumer does a bunch of heavy lifting like talking to which partition, which topic, and so on. So a lot of the work of reading and pulling data and also maintaining state is shipped off to the consumer. The broker doesn't do a lot of heavy lifting other than lifecycle management, like retention window and so on. So Kafka is closer to dumb broker smart client model. RabbitMQ is smart broker dumb client model. Kafka can act as a durable message store, which refers to its retention window. This is extremely important in machine learning data, big data use cases, because you want data to live for a while, because you may even have use cases like tell me trending topics to recommend to a user based on their last 14 days of clicks. That's a very interesting way to look at it. So if you have data available, you can kind of fetch latest 14 days of data and put the trending topics for them and so on. Kafka is pull based. RabbitMQ is push based. Priority ordering is not supported. Replays. So replays are a consequence of retention period, right? So if a message lives longer than just being read once, if a message is living for 14 days, what Kafka is letting you do is replay on the same data again and again. So it can mean different things. Basically, you have machine learning model M1, M2. You can make them read the same data. They will produce same output. So you can replace can help you do such things. Replace can generally help you replicate, go through your log and figure out exact sequence of actions that have happened and so on. So replace is something Kafka can help you do. RabbitMQ won't support such functionality. So just a brief recap on that. I think we are ready to move on to the next component.
Aditya,
yes.
Can you recap on that smart broker or dumb broker, or a smart consumer or dumb consumer? I think I'm not able to recollect. Can you recap just quickly on this?
Yeah. So smart broker in RabbitMQ is because broker does bookkeeping, routing, and kind of deletion and all that stuff. So it manages everything about the message, from where the message should go to lifecycle management of the message. Kafka doesn't do all that stuff in the broker. Kafka doesn't do routing, except that the message will show up in the topic it needs to, and then the consumer will figure out reading from that relevant topic. So there's no notion of routing a message anywhere. Also, it doesn't do things like offsets and so on. So offset is where a consumer has read in the queue is maintained by the consumer. So the consumer is a smart consumer. Broker doesn't take responsibility for maintaining state of messages and lifecycle management of messages. So it's not a smart broker in Kafka world. It's a smart broker in RabbitMQ. In RabbitMQ, the client is a dumb client because client receives the message. It's a push model. So client doesn't care about logistics of where to query for a message. It just knows that it will get the message. In Kafka, you need to know the topic, and the client is smart that it will fetch the message from your topic. It will also keep track of where it is, commit offsets, and so on. So it's a smart consumer for Kafka and dumb consumer for RabbitMQ. And having said this, there are many other products which will follow the same kind of principles. Some may be smart broker, dumb client implementations other than RabbitMQ. There are many other offerings in the market. Likewise, there are many offerings in the dumb broker, smart client world. It's just that Kafka and RabbitMQ are two good case studies to study. Someone mentioned Kinesis. So Kinesis will also be an option, and many other brokers are available in the market.
And the offset you mentioned where consumer needs to take care of the offset is in the case of Kafka, or it's in the case of, because in the Kafka that should take care of by Kafka itself, right? Because you mentioned that there is a dedicated topic just to keep track of offset, right?
Yeah, but the place in line is tracked by the consumer. So when the consumer receives a message, and once you don't have to do all that work manually. When you use Kafka API, the Kafka API will wrap all that complexity behind the scenes, but the consumer is still keeping track of its state in the message queue through offsets.
Okay. So the client side Kafka library is what is actually writing into this offset topic, is it? That is in the case of Kafka, right?
Yes, that's right.
Okay. Thank you.
Okay, great discussion. Thank you for all the questions. So in the interest of time, let's move on to interview expectations. And then we can start solving our question itself. So you all probably already know this from your experience in other classes, but just going through this for completeness. For any system design interview, how I see it is there's depth versus breadth kind of interviews that come up. Which one happens is the choice of your interviewer and how your discussion is going. If it's a breadth level interview, the expectation would be to kind of design different components, talk about responsibilities, pros and cons, some high level trade-offs and things like that. Big picture kind of solution is what is expected in breadth level interview. But oftentimes you may see that some teams need some special level of expertise in some areas. Maybe some team is looking for streaming experts. I've definitely seen such situations. So you may encounter depth level interviews as well to gauge how deep your understanding is. And in those cases, you want to know one or many technologies, how they work in general, pattern wise. You don't need to exactly know how does Flink work, Spark work, Kafka work, all of that. You may need to know one or two based on your experience, but you generally need to know how do such things borrow ideas from each other and things like that. Having said that, implement something that's quick, like in your first 5 minutes. Obviously, you get requirements, gather functional, non-functional requirements, talk through your understanding, and be sure you're on the same page with the interviewer on what you're designing. even if you've seen the question before, it's best to make sure that what you will propose is in line with what the interviewer wants to hear. And then design something that's like a brute force solution or a MVP, similar to your lead code interviews. Quick and dirty, but some correct implementation, and then start scaling up your solution for performance, availability, throughput, all those kind of things. That's the rough flow of actions you want to keep in mind while you do any system design interview. With that, let's jump into our Datadog example, and let's start our discussion. How we want to do this is, let's do one round of gathering requirements first, or clarifying questions, and then we'll be almost at lunch break time. So let's take a break and then come back and flesh out the whole design and talk in detail of everything. So why don't we do this? Let me go back to the example slide here. And let's just talk through some points that you want to bring up as clarification questions or things to keep in mind, or what all will you ask your interviewer. Any things that you want to discuss early on in the interview. So we are designing Datadog-like tool. Our job is to design something that will keep track of 10,000 servers, each of which emits 2,000 metrics per second. And you will eventually build something that will aggregate those metrics by minute. For anything in 2 days window, you want ability to query in two ways: server ID and metric ID. Whichever way you query, you want minimum, max, and average of all metrics. And then you also want to build in time range support. So you can query, give me everything for server 1 for 3 months. In that case, you have to retrieve metrics by minute for all the 3 months and give them min, max, average. So that's the prompt. Any clarifying questions? Yes, Rishikesh.
So one question that I may have based on the problem that I'm reading here is like that I'll say whether the input fields, right, the query fields, are they going to be static or are they going to be changing, right? So that will actually that will help us simplify the API that we are going to write to produce the results.
Okay. Okay, great question. Any other clarification questions?
So currently we are focusing on the system matrices, right? Not the business data or the custom matrices to get the business related data matrices, right? What kind of matrices we are? What kind of matrices which we are going to take care, like
So how I would think of it is, you want to build up to 2,000 metrics capability, out of which some will be system level.
Oh, okay.
And some will be custom metrics.
Okay.
But total 2,000 is something your system will be capable of handling 2,000 metrics a second. What the breakdown is left up to the user. They can have like 1,500 custom metrics and 500 system metrics. You can leave that up to the user of your product.
And the retention, what we are mentioned, the retention of the messages. Okay, leave in 1 year. Yeah, data will leave in 1 year. Is it okay?
So maybe we don't want to think of data living in all that second level data living for 1 year. Someone already asked that. compiled data, like the 1 minute aggregates that you compute, can live for 1 year. Storing second level data for 1 year will be way too much. So you can propose how long you want to store second level data. That's part of the, so how long to keep second level data. That's your choice.
What is the other data which we are planning to store now? I mean, you said this is going to be too much of data, right? The second level. So aggregate data. What is that? Compiled 1 minute aggregate data.
So at you want to return min max average at a minute level for any of these metrics.
Okay,
so
okay,
you
okay.
compute it and keep it somewhere. That can live for 1 year.
Okay. Okay.
Okay, great. Anime, do you have a?
Yeah, I was thinking like if we are keeping 1 year worth of data, won't it also make sense at some point of time to aggregate minute level data? Because if you're looking at a month span, a minute data might be too granular. So is it okay to ask people like to say, hey, at what point of a time would you aggregate a minute data to an hour data? And
That's a good question. But I do see, I mean, if you use these tools, you'll see you have minute level data available for very long periods of time. It's common
okay,
to,
so now that I'm thinking maybe you'll draw a graph and then you could zoom in and zoom out kind of stuff. Maybe that is something that you could try doing.
something, yeah. So something like CPU versus time for the whole of 2022, you'll have Jan 1 to December 31.
Yes.
And you will potentially have like minute level bar charts. You can,
by default, it won't make sense, isn't it? Because if you put a minute level, it will just think for a day, it will be, I'm just thinking out loud, it's like 60 times 24, which is like 1,400, 1,500 points for a day, and then multiplied by 365. So just, I don't know how much is 1,500 times 365, but I'm guessing 100,000 kind of. We have approximation, yes. So we're thinking like, do you need to show all that point, like, or maybe, but we do need. I was just thinking when I was talking to you, like maybe they need a zoom in capability or something.
Yeah, exactly. Yeah, exactly. Yeah. So let's build the capabilities to store it. Like you said, you can zoom into this part and get minute level data. If you zoom out, you get hour or day level data. But also, let's not worry about the front end part. Let's just assume that that stuff is handled, some JavaScript, some front end will do all that stuff. We don't need to worry about how visualization of data works. That's beyond the scope of this part, but we'll design how to store, how the agent will send data, how will you compute data, how will you store data, all that stuff is what we'll discuss.
Okay. So Adi, I think can you go back to the requirement one more time, like the requirement list that you had? Yeah. So one of the questions that I had was like, you had some aggregation based on a time range, isn't it? Like a time window, or you always have the granularity of 1 minute, isn't it? That's what I was trying to ask. And maybe and third and fourth would be exactly the same thing, isn't it? Like when you're giving a time range, you're looking for granularity, or you're not looking for granularity, just looking for min, max, and average value around that time range.
Yeah, let's just say that's also 1 minute. Let's say 1 minute is across the board, you can support 1 minute granularity. Minimum you want to support that. Then if you support 1 minute, you can support higher levels of granularity.
Yeah. No, I was suggesting you were number 3. I'm guessing if you are giving a server ID and looking for min, max, and average, you're just getting 3 data points, isn't it? Like the output.
Oh, so okay.
At least the number 3. Number 4 will be as many as server, but it'll be
no.
No. So you have 2,000 metrics for each server, and if
okay, 2,000. But yes, so 3 times 2,000. Maybe I don't know how you'll represent the data, but maybe one aggregation row for each matrix, and then 2000 of that?
If
I
you
don't know
do
how the
mid
data is.
level by time range,
There is a
if you
time
do,
range,
yeah,
right?
Yes.
So it could be for 1 full year, you can, as much as 1 full year, right? Time range can be.
Yeah, then 1 minute won't make sense, right? Because all you're saying is last month, how much is my min, max, and average on that matrix?
I see where you're going with it. So what we can focus on is, if you're asked the question that for the last month for this server, give me min max average, what you'll produce is every minute for the last month should have a min max average for all the 2000 metrics. Now, whether user wants to see it at a minute level granularity or not is up to the user's choice, but you should have the data available if they choose to go down to minute level granularity.
Okay, then that makes sense. Okay.
Adityan, we can also assume that all the data would be numeric, right? Produced by these machines. So that they can take min, max, and average, right? Because it can't be like some category data or, some yes, no kind of a data.
Yeah, great point. It will be numeric, and part of it will be you can design the payload. So you can think of how to design the payload that will transit, or payload that will move from your system to your consumer and all that stuff, where you can design what you want in that payload. Kaviraj?
Do we have any throughput requirements for these API? Because I'm just thinking, like, you have APIs designed for each matrices. That way, you can max have 2000 specific matrices in your dashboard. So I'm just thinking about, like, loading the page. We should definitely need to get the throughput requirement right, because otherwise it can take a long time to load all these matrices in the UI, right?
Great point. So let's just say, reasonably, as a user of Datadog, you load a dashboard, you can wait few seconds, maybe 3, 4, 5 seconds. One thing, that's a good point. There might be some SLA, but what's more important is hot data loads fast, and hot data is 2 days data. Recent data loads fast. Cold data or less recent data, we are okay waiting a bit longer, but it's not like we'll wait for a minute. Waiting a bit longer, meaning perhaps 1 or 2 seconds more, but we want to build such a thing where hot data will load faster. And that's anyway a thing you will see in APM tools, because if something goes wrong, it's more likely that you're looking at it at recent data, and not that you may not use it to look at very old data very often. But great point. That's a great point to consider.
Yeah, since we have this alerting mechanism as well, I think, like, most probably, like, we will be interested in the recent data, like, if something goes wrong or what is happening right now, right? So I think it's going to be very recent data, right? Okay.
So
Nice.
one quick slide. I have some more questions here. We can just go over those and then take our lunch break and then come back with our design. So few more
One
things.
more thing, Aditya. So this is going to be, like, a distributed system, right? So I'm just thinking, like, is it a requirement? Like, do we need to have a distributed tracing, those things, right? So yeah,
we can skip
because
those
that is very
tracing and logging things. We can skip that part for now, because it may add more complexity to our design. For now, we will keep it to the queries. Time range queries and min max average aggregation. Those are our only two requirements.
And partition, we mentioned that is helping us in the increased response time, or for the decreased response time, or I think but I'm just trying to understand that. So increasing partition is actually helping us distribute the data across or horizontally scale. That is the only advantage which you are getting, or I think are you getting? Yeah, increasing performance also we get as an advantage using partition, right?
Yeah.
Yeah. I'm just thinking like, if you have a throughput requirement by increasing partition, you can actually help get that desired throughput, right?
Okay. Yeah.
Okay. Thank you. Yeah.
Great. Just covering these few more things. So few more questions you can think about is how are the metrics emitted? So who's producing the metrics? Can we assume we have an agent running that is producing the metrics? If so, then how does that agent work and so on? Granularity of metrics expected. We already covered that in 3 and 4 queries is 1 minute. So all queries we execute, we want to see data down to a minute level. A few other things you can ask your interviewer: how many users will use the dashboard simultaneously? This is usually number of employees, because it's usually an internal tool. You don't expose it outside. And maybe more specifically, number of engineering folks, non-technical folks may not be customers of your product. Any queries that are executed more frequently than others. You can imagine any query for recent data is something you would expect to be occurring more frequently than others. We talked about latency, SLA. So we said few seconds at the worst. Nothing very strict here, but just some ballpark estimates. Any need to build a alerting mechanism? You can potentially, let's just say this can, we leave it at potentially if time permits, but that's something we can look at. That's just some things to think about.
One question. So since we are showing all many matrices in the dashboard, right? And normally I feel like these tools, they will have time duration selection at the top, right? So that means if we have if you are changing last 30 minutes matrices to last 1 hour matrice, that means you are actually hitting all these 2000 APIs in one shot. That is what is expected, right? And get the all these 2000 matrices data during that particular event of changing timelines to 15 or 15 to 30 minutes or something like that.
Yes, exactly. Yes.
Okay, so that is the load, which is that is a max API load from a single user we can get in the server side, right? The 2000 API request.
Yes. So yes, that's right. Maximum load for one server will be they are sending 2000 metrics a second. Now, whether they send it every second or they send it every 5 to 30 seconds is your choice. We can talk about that.
Then, here you mentioned that the number of employees. Then we need to ask how big is the organization, for what kind of organization we are building the system, right? So the organization may have hundreds of users, or organization may have thousands of users. That is also an important information we need, right?
It is, although if you think about it, is this system read heavy or write heavy?
Read heavy, right? Oh, sorry, write heavy. Sorry.
Exactly.
Write heavy, yeah.
So if you, so you can think of it, hundreds to thousands of employees may not be a big deal, but it is a big deal for a very write heavy system. So
right. Yeah. Okay, thank you.
Great discussion. Okay, one last question, then let's take a lunch break. Animesh?
Hey, I was thinking like the agent that's running on the servers that is sending the matrix, is it making one API call for each of the matrix, or is it like patching everything in together and then sending it? I never thought about having multiple. So is that a clarifying question that we should have asked?
That's a good question, but I think it can come back to you as you can kind of decide what one API call per call or batch call, and maybe talk through pros and cons of it. So that's your choice.
Okay.
But justify your choice with what you think might be a better.
Okay. Ideally, like it should be batching, isn't it? Otherwise, you're like overwhelming the system with like 2,000 calls rather than having one call.
Exactly. Yes.
Okay.
So we will dive deep into that.
Oh, into the next call. Okay, makes sense.
Yes. So this is the simple diagram we can sketch out, but let's do this. Let's take a lunch break, come back, and then start with this diagram. And then the plan is we'll talk through on a high level, and then we will dive deep into each of these components and kind of flesh them out in greater detail. So we have about 2.5 hours of discussion time on just this part alone, and we'll dive into each of these. It's 12:45. Let's take like a 20-25 minute lunch break and come back, and the class will go up to 2:45 p.m. Pacific time. So let's come back by to 1. Let me put up a slide here. 1:10 p.m. PST.
And Adityan, will you be covering Spark streaming while designing this?
Yes, we'll talk about Spark streaming as well.
Okay. Because it brings a good point where batch, how you send a data batch to batch, probably Spark streaming, I was thinking, but yeah, if you're going to touch,
Great. And if you think of any other questions in the lunch break, feel free to write it down in the chat so we don't lose track and we can address them once we are back.
Sure.
Okay, thank you so much. I'll see you in 25 minutes. Hello, everyone. Anyone back from the break?
Yeah. Yes. Yeah.
Yes, we are here.
Okay. Sounds good. Let's keep rolling. So let's start with a quick architecture for our interview question, and then we can start deep diving into each of these components. And we can obviously take alternate points of view as we deep dive into each of these. But on a high level, my proposal is something along these lines. We have many servers running with what's called an agent. So this everything here in here is our Datadog network, and this is client network. So client has many servers, 10,000 servers, and we offer a agent, which is a software or something that will run on each of those servers. It's basically a process. We'll specify what all the agent does, but for now, let's just say it beams metrics, like it will send metrics every couple of seconds. It will send 2,000 metrics a second, and we'll decide how often to send, but it will gather all the metrics running on this server. So CPU utilization and custom metrics, all of that will be gathered by the agent and sent. Where it's sent is it's sent to some stateless servers or some REST API servers. We don't need to sketch out all the API calls here. We can if the interviewer asks us to do that, but for our discussion, we have a lot of other things that we can dive deep into. But all we need to know is there is some amount of servers here. Maybe there's a load balancer here. What those servers are getting is they are getting a feed of data from all your 10,000 servers, emitting 2,000 metrics a second. Now, these servers are responsible for kind of transforming that data and decide how to publish it, but they will eventually publish it into a queue. This can be a Kafka style disk-based queue for scalability purposes, and we'll design exactly what that queue will look like. The queue is read by workers which are always running. So we'll talk something around streaming workers here. So these workers are always running, and their job is to read the message from the queue and compute aggregates. So they will compute min, max, average, and so on. And then they will write to the DB. And what DB we'll decide later, but they will write minute level aggregates to the database. They'll also write minute level aggregates to a cache as long as the data held there is 2 days. So there is a cache that holds 2 days of data always, 2 days current data. And then finally, we have user-facing servers. And what these user-facing servers do is they are basically contacted when the user loads the dashboards. This is in the browser. User will load the dashboard. That dashboard will talk to some user-facing servers, which are again REST API servers. And these servers will decide what to do with that query. If it's 2 days worth of data that the user is querying, it will look up the cache and return. If it's more than 2 days of data, it will look up the database and return your calls. So this server will orchestrate all the read operations. That's the high level system design. We obviously want to delve deep into each of these components and talk through their design decisions. But any questions or comments? Yes, Kaviraj.
Yeah, I'm just thinking because here we are mentioning that stateless servers. So instead, if we can say that, okay, this is metric collectors, right? Or this is kind of a query service, or I mean, instead of giving this, okay, we will have a set of servers here. We can say that this set, okay, because we are showing 2 separate squares there, we can always say what is that component is doing, right? That way it gives more details about the system, right? In normally that is how we put our architecture diagram, right? What it does, that particular component.
Great
Right.
suggestion. Okay. Great point. Yeah. So these servers are somewhere your metric collectors, and these servers are your query service or query path servers of some sort. But yeah, great suggestion. I'll probably edit my slides after the class with that.
Sure.
Thank you for that. Syed?
Thank you. I just want to make sure I understand correctly. In the first stateless servers, we have some CPUs. And in the last stateless servers, again, we have some CPUs. And the workers are basically, again, doing some CPUs. Can't we just put them together as one servers, basically based on the time it switched between these tasks?
I see. So you can put them as one server, but there are benefits of putting them as separate servers. One benefit is it gives you a lot more scalability. Also, it's a one responsibility per server, which means these servers specialize in collecting metrics and publishing metrics, and you can grow those servers arbitrarily as your traffic warrants it. These servers specialize in computing aggregates of the metrics, which means if you have more data, you can add more of those servers. If you want more than min-max average, you can include those functionalities like percentile calculation and whatnot. You can compute a lot of more aggregates. And these servers are specialized in figuring out whom to query based on what the user is asking. You can obviously make one monolith service, which is what you're proposing, but the con is it will be a bulky one server with way too many responsibilities. And in fact, it will also be a little less scalable and not meet like a very, very big data scale use case.
I see your point in general, but I think the only important benefit of it, which I'm trying to mention, is like, let's assume 8 a.m. Many people come to query and see the dashboards from, for example, yesterday, right? So in that case, the last stateless server is going to be heavier just at 8 a.m. The rest of the day is just doing nothing. And then it can help the other two servers to do their jobs. You know what I mean? It just makes it like a shared source of resources. And can be like, I understand this, like working, for example, with Databricks, I understand they're elastic and you can add servers, but it takes time, like adding servers, the cost is not always linear.
This is logical diagram, right? You can have this metrics collector and query service, at the time of deployment, they could be on the same box, right? But this is just, I think, a logical diagram. It's not the exact.
Deepak and Syed, I think in our previous class there is a suggestion mentioned that based on based on certain situations we should choose, like have separate instances for services. One was like the services are drastically two services. One both are the request volume is high in both cases, then it can be together. If the request for the both services are drastically different, then it must be designed as a separate services. You remember that in our time test, he mentioned that he also mentioned there is a specific architectural pattern name, CQRS or something he mentioned that. So in that it is mentioned that these are the criteria we should use and identify our services are having a lot of requests. Both the services having a lot of requests, then it can go in a single server instance. Otherwise, if it is drastically different, here I am saying that the first server, stateless server, which is basically a write heavy service, compared to our query service, which is basically a read service, which drastically differ in the request, right? So I hope, I think that that way we should separate it out so that we can scale them independently. That is what I'm just thinking. Yeah,
great discussion. Great. So, yeah, there are pros and cons and different points of view, but I agree. You can have them in the same box. You can have separate services. They all have their own merits and consequences as well. But having said that, let's continue with the discussion. With for now, my solution will assume different services. If you want to co-locate them and in one box in a deployment, that's also feasible. But for the purposes of this discussion, let's assume they are different services on different machines altogether. And that's how I'm leaning towards that, but we can obviously kind of have different points of approach on it. Having said that, let's start with the deep dive. I think there is quite a bit of content to talk about in each of these, and each will warrant its own merits and demerits. So why don't we do this? How I like to do this section is deep dive into starting with the agent. We deep dive into that and look into what it looks like, encourage some discussion from all of you, and kind of summarize different points of view on how you want to implement the agent. And yeah, that's basically the takeaway. There's no one right answer, but there will be many answers with their own merits. So let me put it this way. Let's start with the agent, and this is my understanding, and I'll pose some questions and you can all take turns to think out aloud. What the agent is, it's a process running on each server. So if your server itself is Amazon order server, then you have some order service running. In addition to that service, there is an agent running on that same machine. This agent receives 2000 metrics a second from the primary service that server is responsible for. What this agent then does is publish metrics to some endpoint. Let's not worry about where, but it will go to our metrics collector server. Now I can post these questions as open-ended. So one is, how often should the agent publish? Then what should it do? Failure scenarios of the agent. What else can we think of? How does the agent recover from failures? Perhaps let's just start with these two. So there was some discussion on one API call per publish versus batch publish and all that. So what do you all think is what's your viewpoint on how often should the agent publish? Remember, this is different from how often the agent receives. The agent receives 2000 metrics every second. That's a given because that's what it's collecting. But now, how often should the agent publish? We don't need to worry about API sketching of the agent and things like that. That may be a bit distracting from our real-time discussion today. But those are also perfectly reasonable questions to come up in an interview. But let's talk about how often the agent is publishing. Deepak?
Every second.
Okay.
1 minute. Every 1 minute or 5 minutes.
1 minute or 5 minutes. What are some pros and cons between every second to minute to 5 minutes?
So I think we should go with the seconds, because if there is a failure, then we should not miss that failure, right? And it may last for seconds, right? And we should immediately get that information, because we also mentioned that these systems, they do notifications, right? So we should get the immediate notification. Based on that, we can take decisions, or automatically curing the system or something like that. But we should get the notification as quickly as possible. So we should not be waiting for minutes, right?
Okay, so you are leaning towards every second for quick notifications.
Right,
okay?
Right. Yeah.
Shia,
And failure.
Sorry.
I was going to say.
I think it would be better if we can first quantify the size of the messages, so that we know exactly how much it is publishing.
Okay, great suggestion. Quantify size of the message. While that comes up, you can also think through what the payload structure will be, since that has already come up. Design the structure of the message.
Yeah, it would be machine ID, server ID, metric ID, and then maybe need to include a timestamp, and then the data, the metric.
Okay, great point.
So this should be a time series data, right? I'm just thinking like, how this time series data will be normally sent to a time series database. Is it just the timestamp? Is that what we normally send? I'm not very sure about that.
Sounds good. We'll talk about that. Let's keep using the raise hand feature so I can make sure everyone gets a turn as well. Let me ask Shia, did you have something to share?
I was just going to say, like, I think a lot of this largely depends on what the requirements of the system are, right? And I think it kind of goes back to like the quantity, the size. Do we need to have updated metrics like every second, or is every 30 seconds good enough, right? And then it will, like, how often we publish it will also dictate possibly how large like the rest of the system needs to be in terms of its ability to handle that many requests or that many API requests, right? So I think like all of it just we'd have to go back to kind of like what our functional and or non-functional requirements are, rather than like this every 30 seconds is best, right? Or is that not the right approach?
Sounds good. Great point. Animesh?
I had a similar viewpoint. Like, it all depends on the service level agreement, isn't it? Like, there could be some places where we would like to figure out whether the server is down and how fast we want to react to it. But every second is like too much, like a call. I'm more towards batching the job. I don't know whether 5 second or 10 second is would be the optimal number. But I would, unless we have a very high need of responding within a second, I would like to keep it under a second. That's what I was thinking about.
Sounds good. Deepak?
And what other part was like, what in case of failure, I think agent, I'm guessing they are, they will have the state so that they will store the data, and once the agent recovers, it will be able to store that, send the backup data back to the server.
Okay, agent stores state. Okay. Sounds good. And recovers. Deepak, did you have something to add?
Not really. I kind of agree with Animesh. It definitely, it can't be 1 minute or 5 minutes. It has to be less than 1 minute. Like, it may be like, if not every second, maybe every 5 seconds or 2 seconds or 10 seconds. I don't know what is that. But the thing is, if we look at 2000 metrics, and if we look at these fields, right? So either 16 bytes into 2000, that's like 32 kilobyte. And that needs to be sent per second, right?
So 16 bytes, 4 bytes per second. We are getting 2000 times 16 bytes.
Yeah, 32 kilobytes, right?
Okay, from one server. So from 10,000 servers, we are getting 330, whatever this number is.
320 megabytes.
So that's our throughput from all of our servers, which will eventually show up in the queue. But great point. This is coming up now. Okay, so yeah, these are.
Can I say something?
Yes.
So what I'm thinking, considering, so we have this a situation of failure, right? So I'm just thinking, like, if we go with the single second approach, like 1 second or 2 second, then even if there is a failure happened, I think we don't have to be so much worried about it, because that in the next second it is again going to report, right? So we can completely ignore, I believe, that message, which we have an error in generating message or something like that, right? So I feel like going with a lower number will help us eliminating these kind of failure scenarios.
I see. Okay, great point. So let me summarize some of this discussion, and then we can talk more on the failure scenarios. So how often should the agent publish? Of course, I was not looking for one number, but that exact number is of course like something that you determine based on user requirements and potentially cost per call and things like that too. But generally, what is the sentiment on how very often to less often? What are pros and cons? If you publish very often versus less often, there are some takeaways. That's the general theme. Very often might overwhelm services. Very often is subjective, but if you did every second, it can overwhelm services on your metric collector service and things like that. And perhaps you don't need that many calls anyway. You don't need one call per API, one call per metric or something. You could get away by batching calls. That way you're making less network calls. So less network calls. And less network calls means less network IO and things like that, and potentially not overwhelming your downstream services. If you make less often calls, which is subjective again, but at a minimum, you might have to do it less than a minute because you want to support minute level granularity at least. Perhaps you can get away doing more than a minute too, but I would recommend something that's a balance between finding out something happened in your infrastructure quickly enough and not too slow enough as well. So if you make it too less often, like 5 minutes, then you're delayed to find out something went wrong in your infrastructure by that long. So it's like a balance as well there. What else? So batching calls is something you can do, which is a good idea. What batching will mean is, let's say you, for example, if you decide publish every 5 seconds, if this is the decision you make, then what does it look like to publish data every 5 seconds? What it means is you will publish a list of metrics for those 5 seconds. So you'll have first, second, third, fourth, and fifth. Each second will have 2000 metrics here. So in total, you would be actually publishing 2000 times 5, which is 10,000 metrics will be published when you do this one call, when you make one publish call, which is reasonable. You can just compact the metrics, kind of serialize them or something and send them all in one batch call. And each metric is looking like this, as we already talked. Each metric, each payload is the four valued payload: server ID, metric ID, timestamp, and value. All are 4 bytes long. Timestamp is the origin time at which the metric was sent by the service, like order service. Whenever it sent a metric, that timestamp will carry the value when the metric originated. So something like this is the kind of rough idea. How you potentially actually determine this when you design it, it would be a combination of many things like user requirements, cost, some heuristics, and whatnot. And potentially there's no one right answer either. Perhaps Datadog or Prometheus and other solutions might even let some capabilities be configurable as well. But those are all some ideas to put out there. That's the summary of that. But okay, let's talk about failure scenarios. What kind of failure scenarios can you think of? What can go wrong? Let's summarize what failure scenarios and how to recover from such things and how much to recover. Someone said you can ignore a message if it's failed to send. It's fair. Big data system, we talked about fire and forget. It's not super critical to get CPU usage for every second. It's potentially okay to drop a couple of metrics here and there, but definitely there's some SLA that you can't like drop 50% of the data. You potentially drop very, very less percentage of data. So for the data, we are still gonna try to recover from failure. So what are some scenarios where you see failures happening and how can you recover from them? Deepak?
So all these machines, the servers on which this Datadog agent is running, they must have a failover mechanism in place, right? So So the whatever it is, active, passive, or whatever failover setup they have. So the second server would come on if the first server dies, right? So this thing would continue, but with the whatever interruption it would have, right? In terms of howsoever long it would take the backup server to kick in, right?
Okay.
So that would be noted, and the matrix, the display, the Datadog display would tell that story, right?
Mm-hmm. Okay. Fair enough. So the server on which Datadog is running can itself go down. That's one failure scenario. What other failure scenarios happen? Animesh?
Well, if the agent goes down, then I'm sure there is a backup for the agent as well, right? There is a failover thing, and that would get reflected in the similar manner.
Okay, agent is down, but server is up. That's one possibility.
There could be a network partition. I was thinking like maybe they won't be able to communicate with so whenever a network comes up, they should be able to relay the data.
Network connection lost. Okay. What else? Any other ideas? What all can go wrong? Kaviraj?
Yeah. So I'm just thinking, like, since you, since we are batching this request and this matrices and sending, right? As when we are talking about, okay, we can have 5 seconds or more and gather all those matrices and send in one shot, right? So I'm thinking about these failures, such as, like, a memory error, for example, like, out of memory error, which is caused because of a particular file upload, or so I'm just thinking. So if there is a memory error happened, then the instance may go down at this point in time, because instance may restart, and this information is passed after 5 seconds or later. Then you are actually, if you have a scaling based on that, right, you are actually losing time, right, to get the new instance, because you are already late, 5 second late to create a new instance, right? So I'm just thinking on that direction. So
Great point. Sounds good. So this is a good list. We can just quickly run through some of these scenarios and just talk on a high level what can be done to deal with them. The point is to just think of these things. This is the distributed systems problem. So server on which Datadog runs can go down. That's possible. And how to solve it is, of course, this is not from the perspective of Datadog, it's not Datadog's job to restart that server. That server should itself be having the capability to maybe come up again, or maybe there's another backup server that comes up, whatnot. Datadog can at best do some alerting. That's something it can do. So maybe it sends another metric, or the metrics collector service realizes it hasn't heard at all from some server for a span of 30 seconds or 1 minute. So it does keep some track of health of the server, and if it's gone, it can alert. That's one way. Agent is down, but server is up. This is possible. So one possible way to keep you want to try to keep agent running. That's the solution. Try to keep agent running. Now, how to keep in practice, you may see things like supervisor task or something. Supervisor task means it's another task meant to give the agent high availability. So the sole purpose of the existence of a supervisor process is that it will keep running and it will keep supervising if the Datadog agent itself is running, and if it's not running, it will restart it. Thereby it gives some high availability. Now supervisor itself becomes a single point of failure in some ways. If supervisor is down, there's nobody to restart agent, all that issues follow. But that's just one thought there. Network connection.
Like Kubernetes, you could use Kubernetes and Dockerize these agents and have like for both of them, even on servers, right? If it's like auto scaling, you can do auto scaling, and the first one alerting the Datadog. The Datadog server itself, it's like if you put in auto scale mode, if it fails to collect, you have one more getting spun up because of a failure, like on server.
Yeah, great point.
And also one point when I was thinking about the earlier one, like the previous page, right? Like 1 minute collection or like these logs, right? These logs, like all these logs are agent is just collecting the logs, okay, and sending this as a batches, okay. Now you could still rather than sending every 5 seconds or 10 seconds, which is a network hit, right? You can the reason behind I'm thinking of 1 minute is these logs are written in their own respective logs. Like for example, like event logs. My Windows operating server, they have their own event logs. And agent, what it's doing is trying to pull these logs from them, right? And trying to push it to the service. So you still have these logs there. It's not like you're losing the data. It's just batching it and sending it. You don't need to send it every 10 seconds or 15 seconds or 30 seconds to overwhelm the network. Okay, you can still wait for 1 minute and send it, but these logs are still present. Like all these 2000K matrix, all the system will have its own logs. Even application server has its own logs. You take it, you wait for them, take it, and then send it, and then you can show it. Because in cloud also, right, AWS cloud also, you have detailed logging and you have instant logging, 1 minute and 5 minutes. So they might be waiting and then sending it because of the activity logs or whatever they'll be doing it. So I feel still you could still wait for 1 or 5 minutes. That's the reason why I gave that numbers, because it's not agent collecting the data. It's agent is reading from all these logs and aggregating and sending the data.
Great point. Great. Yeah, that's also a good alternate opinion there.
But in case of this memory out of bound, right? That agent cannot read that data, or system cannot really generate that logs, right? Because the system itself is down now, right? How it is going to write that? Because
the system is down at that time. So system is down. So another system gets spun up because these are so that.
But that log is lost, right? You don't have that log written anywhere or persist anywhere in the file system.
Out of memory, just you ran out of memory. When you start it, the logs are not going to be deleted. It is going to persist in the same machine. Like out of memory, if you say, it just ran out of memory, okay? And system crash, and if you start again, the logs will still be there. If you go to event logs or something, you still have these logs. It will not be lost.
The logs are on disk, is what you're saying. Logs are.
No, but what I'm saying,
only disk crash won't be. I'm not sure. Disk crash happens. That is a scenario, but not in the out of memory scenario. Because they're not written in memory. The logs, right? These logs, event logs, all these Windows event logs, they're not written in memory, but they're written in probably disk. Yeah, disk goes down. I'm not sure what to do, but yeah.
Great. Yeah, this is good discussion. But in the interest of time, what we want to do is we just want to bring up these, just talk through them. If we can, there's a lot that goes into just designing one agent. We have many more components to talk about, but it's good that we brought all this up. I just want to quickly summarize 1 or 2 more things and then move on to the next component that we want to deep dive. So we talked about agent down, network connection lost. There are potential things here, but if you use reliable protocols like TCP, you are good. If you use UDP, then you have to potentially encounter issues like how to retry and things like that. But if TCP is what you're doing, then it's guaranteed your the data that you want to send will eventually reach and acknowledge and be reliably sent. One last thing which we can discuss is how do retries happen? How does if network connection is lost, the agent is going to retry after some time, and network is alive. But a popular interview question is, how would you implement retries, or any ideas on best practices for retries?
One thing on a network connection loss, right, Aditya, is like you have a load balance, and they are all stateless servers sitting behind. So will the load balance? So these are all stateless, right? If it comes back, if the server comes back, they'll all send the data back again, right? So there is nothing, even if the network gets lost. Like for example, load balancers are not single point of failure. They'll have their own replicas where it can send it to backend servers. But if at all it gets lost and comes back, then you can send it back, right?
Yeah. So sending it back will be a retry, and the retry is basically the agent transmitting the same data again because it couldn't successfully send that data that it wanted to send. Any ideas on best practices for retries?
I'm thinking.
Sorry, just making sure everyone has a turn. Karthik Bhojan, if you have something to share, please feel free.
Yeah, so probably we can do a health check, or maybe ping, keep pinging on to make sure that it retries.
Okay. I'll check and. Okay. Any other ideas, Deepak?
Well, yeah, I was going to say that, you try initially for a certain number of times. If it doesn't connect, then you try it like a little longer, time apart, kind of a thing. And then eventually, after you have made enough effort, if it doesn't work, then you stop.
Okay, great point. Eventually stop. So what you've described is, I think that's what I was looking for. This is basically what's called exponential retry with back off and jitter. So the reason I bring this up is this is a very common pattern. You might see it many system design interviews will potentially quiz you on this. So retries are a very standard. It's a solved problem at this point, I would say. And the best pattern out there is what's called an exponential retry with back off and jitter. What it means is, how it works is, think about it this way. Now there are 10,000 servers running agents. So A1, A2, A3, and this is your metrics server. And each of this is trying to transmit data. This network link can drop. That's one source of a retry. The other retry could be, maybe you somehow hogged up all the bandwidth on this server and this server is unable to do anything. So what is needed is, when you implement retries, it's not good practice to allow all the agents to retry at the same time. If they all retried at the same time, you're basically again sending way too many requests parallelly to the server. A way to solve that problem is to kind of separate the time at which retries happen by using something called exponential backup. So server 1 will retry at time window 1, first second, and then it will try again. If it fails, it will try at 4th second, then it will try at 9th second. Now let's say server 2 retried at 1.2 second, then it may retry at 5 second, and maybe it will retry at 9.5 seconds, something like that. So by doing this, what is being avoided is making sure two servers don't end up retrying at the same time. And this randomness aspect is what's called jitter. So there's some randomness built into every server's retry, and every server will exponentially decay the retry, which is, it will not keep retrying if it's getting an unsuccessful response. It is going to give it a little more time, which is dictated by some math function built into it. Usually it's exponentially decaying. So it'll slowly ease out the retry, and eventually, maybe perhaps 3-5 times post that, it might just stop and drop the data altogether. So that's how retries work with exponential backoff. And I think that's generally the kind of nature of problems you'll be solving if you were the engineer designing the agent or implementing the agent. Having said that, there's a lot more you can talk about here, but we should contain this for the time and move on to the next component, because we have equally enough amount of tech deep dive to do in all the other components. So any quick closing comments on the agent?
Yeah, one quick question. So now we are assuming that the agents are pushing the messages to the metrics collector, right? So we need to also know, agents should also know that when it stops sending the data to metrics collector, from that onwards, he should get all the matrices and send it to metrics collector, right? So that part also needs to be taken care, right? Because maybe one minute back is the last time when he sent the metrics to the metrics collector, right? Now he's ready. He's having a successful connection and he's ready to send matrices. So he needs to send the metrics which he gathered 1 minute before, and from then onwards, all the matrices needs to be sent to metrics collector, right?
Great point. So you're saying cache the unsent data on the agent for some duration until it is sent. This is also a good point, until it is sent. There might be only so much you can cache. So maybe you can keep caching the data that you want to send. An agent will eventually send it. But if the whole instance is down, then that cache itself might be lost. But you can keep caching the data that's not sent and is scheduled to be sent. Maybe write it to a disk or something and keep a track of where it is. That's a good point as well.
But this is very important because otherwise we cannot, say that this is a, maybe a consistent system. Maybe like, during this time, if there is a failure happened in this particular instance and you are not really reporting it, so you cannot really we cannot really say that it's a reliable system. We cannot really rely on this metrics, right? So we cannot achieve that reliability part, right?
Great. Agreed. Sounds good. Okay. So let's move on in the interest of time. If there are some more questions, please feel free to leave it on the chat. But let's continue talking about the next component so that we have enough time to talk about all the components. Okay, so what's happening next is this agent has sent the data to the stateless server. Stateless servers or metrics collector service has received it, and it's received the data and it's going to publish to the queue. You can do a lot of discussion on this part as well, but that's kind of common between other system design modules. So maybe let's focus our energies on the real-time components here. That will be the most value of this valuable discussion here. What all we can leave this here is these servers are going to publish data to the queue. They are going to do some kind of massaging of the data, and I'll describe that in the queue. But let's start here at the queue. What we did some back of the envelope calculations, but let's start there and figure out what's happening. So queue receives, what is the throughput in the queue? We already calculated this. So there are 2000 metrics a second times 10,000 servers times 16 bytes. And we said it's 320 MBs a second. And remember, this is our payload. Payload is server ID, metric ID, timestamp, and value. This is our 4-valued payload. Let me zoom out. 4-valued payload that's traveling, and it shows up in the queue. Queue is seeing every second we have 320 MBs of data being written to the queue. what is this queue? We are thinking of it like Kafka style queue. You can choose whatever you want to, but because we discussed Kafka, let's use it here for our use case. So if we were to use Kafka style queue, how would we configure it? How many partitions? That's one question, partitions. And before that, how many topics? And what are the topics? In fact, what are the topics?
How about the brokers? How many brokers?
Okay, how many brokers? So, okay, brokers, I guess, is a number of brokers is a choice you can make based on how to kind of manage the whole infrastructure. Can be 2, 3, 5 brokers. But more importantly, once you have chosen the number of brokers, how will you choose how many topics or what each topic will contain? Any thoughts on that?
Topics could be the metrics, right? The 2000 metrics we have. Each metric has its own topic.
Topics, one for each, 1 to 1 for each metric. Great idea. So one topic per metric, which means total you have 2000 topics. I think I agree with this. This is a good idea. And pros and cons again. So you can have one topic with multiple metrics, or you can have one topic with one metric alone. What are some benefits of keeping one topic per metric alone versus maybe not some good benefits? What do you all think? Animesh?
I was thinking like our choice of topic wouldn't depend on how we are batching the data, because if we are batching the data, are we expecting our serverless component to or those stateless server to take a message and divide it into the 2000 topics? I'm not sure how that with one message to 2000 topic will happen. I was just thinking it'll go. I was thinking partition would be done based on a server name or some other way to like divide a consistent hashing to say 1,000 of them, 10,000 of them can be evenly divided into some partitions. I'm not sure how many partition, but 3 or 4 partition based on just the name.
I see. Okay. We can talk about that. But remember, one message will only go to one topic. So it's not like a message gets split into 2,000 topics. There are 2,000 metrics coming in. And the idea is there is each metric has its own metric ID, and each metric, let's say CPU is a metric. So the proposal is we'll have one topic for CPU metric alone, one topic for memory metrics alone, one for
So that's what I was thinking. Like, so when you get a message from the server, so you're getting. I'm thinking one message is coming in. Maybe a JSON document, as like Deepak was mentioning. We'll have a server name and a timestamp, and then key value pair to say, hey, what matrix and what's the value. So those are like 2,000 of those. So I'm thinking now somebody has to read that thing and divide the whole message and divide into 2,000, like 2,000 pieces, like one for each topic, isn't it?
Yes, exactly. And that's your metric collector service will do that.
Oh, you're thinking about the stateless, the servers that are sitting there that will do it, is it? Okay.
Yes.
Oh, okay.
Metrics.
So again, I don't know whether we should have talked about the data server, like the data, how are we going to store the data? I was thinking we'll store the data together, but if we divide into different topic, does it even make sense to like store the data together?
Store the data together. Okay, yeah.
Like sure. I mean, the reason I was saying is, will it be will every second data will store into one storage, or will you have a separate column for each of the topic, each of the matrix? Like I was thinking, is it as a key value pair kind of stuff, or is it going to be each column for each matrix?
Great. Yeah, we are thinking I'll introduce some key value pair. That's my proposal, but we can have one column per metric. We can talk about those as well, but yeah, good point on that. I'll be leaning towards the key value pair kind of setup, and I'll try to give you reasons why that might be a better idea.
Sure, that sounds great.
So you are saying then in that case, then you would have 10,000 topics for each server?
2,000 topics in total.
No, 2,000 one for each metric, right? But you can also have 10,000 topics, one for each server.
Oh, no. The reason I was saying is like maybe we have 10,000 servers, isn't it? Like we could have a consistent hashing to say those 10,000 can be divided to 5 different topics through consistent hashing. So you just say, hey, maybe the server names will be somehow a way to, because all we are trying to do is distribute the data into different storages, isn't it?
That would be too much data per topic. If we have
not per I wasn't thinking about topic. I was thinking all the data will go together, but each server will go to one of the partition. Like somehow we will be able to partition the 10,000 server into 4 different topics or something based on some hashing algorithm that we can come up with.
Solution out, and then maybe we can discuss that out so everyone's on the same page. So let's do this. I like this proposal, and I can just briefly talk about pros and cons. So one proposal is 2,000 total topics where each topic maps to a metric. What that means is CPU metric will have tCPU topic. RAM metric will map to a topic of its own, and this is a Kafka topic. Why this is a good idea? Why is this a good idea is because eventually what will happen is you can scale topics independently. And when might you need to do this is CPU will be a commonly used topic. Every server will have CPU data for sure, which means it's a very high volume topic. So you can potentially provision more resources to meet the demands of a CPU topic, whereas a custom metric like orders successful, this is a custom metric that will have its own topic, TO, but it may be compared to CPU, it will be a less traffic topic. That's one thing. The other is schema evolution is possible easily. What I mean by schema evolution is if you decide that I want to have more than 4 fields in my message, for some reason I want to add a 5th field in the CPU message payload. If you have one topic per message, it allows you to evolve the schema of your payload little more easily with lesser pains compared to having one large topic with all the metrics pooled into that one topic. So you can, the parallel other alternative is you can have one topic or 10 topics, for example. One topic means it would just be one giant topic where all the metrics are going in, CPU, RAM, and custom metrics. All the stuff will go into this. And then what the consequences of choosing one topic will be, workers reading from topic are complicated because they have to now decipher each data point they read. They have to decipher which kind of data it belongs to do their aggregation. If you have one topic per metric, workers are less complicated. There will be some entities reading from here, and they may not be as complicated to maintain because they can just read CPU topic and reliably get a stream of CPU data points and then just compute min-max average. In this world of one topic, they'll get CPU, RAM, and all other data points. Then they have to decipher and they can't aggregate CPU with RAM and things like that. So they have to keep it separate. Those are some pros and cons. In general, for interviews and also for real life situations in companies, you will see a topic is almost like a business entity. It's almost like any higher level business entity can be put into a topic, and that's usually a good idea because you're not only doing this for the short term, in the long term, you can evolve the schema and so on. So a lot of things get taken care of and will be far less headaches to deal with down the road if you don't pollute one topic with too many kinds of data. That's that on this. Let me talk about partitions and then we can take some more questions and thoughts. So how do we decide partitions? How many partitions will each topic have? So one rough way, and this is just one way, you can do it in any other ways. There's no exact answer to this, but think about it this way. Each topic or the whole Kafka queue is seeing 320 MBs a second of write throughput. Now, Kafka is disk style. So at the end of the day, all this data is getting written to disk and there will be files on disk. Now, if the spinning disk will have some write capacity. Let's say the best in class spinning disk does 100 MBs a second. If that is the case, if the best in class spinning disk does 100 megabytes writes per second, then you can't possibly write all your 320 MBs into one partition alone. You need at least 4 partitions. 320 by 100 will be 4. You take the ceiling of this. So you'll need at least 4 partitions. Maybe you can say 5 partitions. So that's one rough calculation to come up with number of partitions. So what are we trying to say here? We're just saying if we support 5 partitions per topic, then with a write volume of 320 MBs a second, our Kafka will keep up with the writes coming in, and each write will eventually get written to disk and it won't get held up anywhere. That's the high level idea here. You can propose 5, 10 partitions and so on. That choice is yours, but you can kind of come up with some rough numbers some way, and this is one way to come up with it. Okay,
so
let me stop there. Yes.
Don't we need to take into account storage requirement here? Like how long are we going to store this in this Kafka for queue for 1 day or 1 week or should that be part of calculating how many disks we would need, or it will be just based on the write rate?
That's a good idea as well. So storage can be part of how many partitions you can need. Basically, maybe you have some, each partition will be a node, some kind of, in AWS terms, EC2 node or something. So each will have some disk space. Let's say it has 1 TB available disk space. Then what you can do is estimate how long you want to store data. So you will have 16 bytes into, actually you already know it's 320 MBs a second times 60 per minute times 60 an hour times 24 in a day. Whatever this comes out to is your storage in a day. And then if you said you want to store for 14 days or something, that will kind of give you the total size. And then you can divide this whole number by how much disk space will each partition have. So if it's 1 TB for some reason, then this will give you number of partitions as well.
This is like more than this is a big number.
Yeah.
This is almost like 420 partitions. Right?
420. I see. So it's total, by the way, it's across everything, all the 2000 topics. So it's not 420 partitions per topic.
Oh, okay.
It's totally 420. So
sure.
Yeah.
Sure.
But that's another way to estimate the number.
Okay.
Great point.
So we don't need to figure out how many brokers. Let's say, can we have this thing on one broker, or we'll have to have broker based on the number of on the storage requirement?
So broker is just like, I wouldn't think of broker as much as partitions. Broker is kind of the universe of
the node, right? Broker is the node, right? Each node in the cluster.
Each node in the cluster. I wouldn't think of broker as each node in the cluster. The broker is kind of multiple things. It's more like a logical construct than anything physical in the cluster. It encompasses many things like
Okay.
there'll be replicas and, but effectively what you're trying to get to is you're trying to ask how many nodes will be there, which is equivalent to what we just calculated. This number of partitions is what you're trying to ask, how many nodes
so
will be there in
that's the number of nodes. Okay, five boxes.
Broker will be similar to this one, right? Like a Kubernetes cluster. You need only one, right? Which will be self. So it will have multiple inside it, but only one cluster would be required for at least a region, I would say. But
right, exactly, yeah. But yeah, so to your point, number of nodes is what you're trying to calculate, and this is also one way to get to that. Okay, Karthik, do you have something to share?
Sorry, which Karthik? I think there are two Kartiks. I didn't raise my hand.
Bhojan, let's see your hand.
No. Sorry.
Okay, sounds good.
Can I ask one question?
Yes.
Yeah. So these 320 Mbps which we have calculated based on the 2000 matrices, right?
Mm-hmm.
But we also said that for each matrix we will have separate topics, right?
Yes.
So what I am assuming is that, for each topic we will configure partitions, right?
Yes.
So then in that case, for each topic, how many partitions? Because we can only have a single partition, right? Because here it's a time series data. We need to get it in the correct order, right?
Mm-hmm.
So I'm just thinking, so 2000 matrices, 2000 topics, and we can only have 2000 partitions, right? Even if it is 320 or more, we can only have 2000 partitions, right? I mean, each topic, one partition, because the data should be a time series data, and basically we should keep the ordering. So I'm not getting that this partition calculation, how we are going to use it if we go different partition for a single topic based on the the volume of data. If that is the case, then you will not get ordering right in the correct way.
Yeah, great point. On ordering, we will try to solve that on the worker side of things. Let's see what we're trying to do here.
Okay.
Yeah. So a node, there will be many nodes, but one node can have topic CPU partition 1. It can have topic RAM and partition 1, and so on. And this other node can have topic CPU replica 1. So partition 1's replica might be here, and this RAM topics replica 2 might be here, and so on. But in terms of ordering, hold on to that thought. We'll talk shortly about the worker, and we'll look at how to fetch 1 minute worth of records, and how to order, kind of calculate your aggregates with ordering somewhat in mind.
So yeah, I think the confusion was like, so the topic should come under under the partition. We should have topics in our previous diagram. Under a topic, we have partitions, right? Or some that is why I got confused. Here, for us, for a partition, we can have multiple topics in it, right? Because
Yes,
here,
yes, yes. You can
CPU,
have-
yeah,
Yes,
yeah.
exactly. Yes.
I think in our previous diagram we put that, even I think even a single topic can have multiple partitions. So other way around also possible, right?
In a single topic, you can have multiple
Partitions also, right?
In a node, you can have multiple partition of different topics.
Because in your previous slide sometime back when we were showing partitions and nodes for a single in a single topic we are showing multiple partitions and the consumers are reading from multiple partitions, right? I remember sometime back we had that slide.
Let's hold on to that. I think it will get more clear as
Sure.
we discuss the next few topics.
No
I
problem.
think
No problem. No.
So far,
yeah, this one is clear. Yeah.
Okay. And I'll try to include that in the workers discussion as well. But let's also talk about the workers, and I'll take some more questions. Hold on to your questions if you or write them down on the chat if you so you won't forget. But workers, this goes hand in hand with the workers. I think that will complete the understanding. So we are here right now. We have 2000 topics, one per metric type. There are some workers reading the data, and we want to just describe the responsibilities of the worker, what they are. And here's where we can talk a little bit about Spark streaming as well. What are the workers? What are the workers? How are they work? Kind of flow of actions, and let's just describe these, right? So what are the workers? In one example, one concrete example is these are streaming workers. And by streaming, I mean always on workers. That's what streaming technologies generally enable you to do. And one concrete example of these workers is a Spark streaming implementation. I can talk through some experience here, but we don't need to confine ourselves to the technology. But in general, we can talk through what the workers will do and how Spark streaming will actually help you solve those problems. So you have messages coming up in this queue, and you have a worker service. More than one of these exist. What these worker service does is, this queue looks like many seconds worth of data is there. There is first second, third, to 60 seconds, 61, and so on. What the worker does is it reads a window of 60 seconds data. And this is possible using Spark streaming. That what you are reading is a window of data, which is called the micro batch. So you read 60 seconds worth of data from here to here from a topic. So you're already looking at one topic. Now, when you read 60 seconds of CPU data, what happens is you will have 60 data points and the worker will run aggregate. So it will do its flow of actions will be read window of data. Then it will run aggregates. And how will it run aggregates? It will initialize min, max, average. Average will be 0, max will be negative infinity, min will be infinity. And it will start running aggregates based on each data point. So it'll iterate through 60 of those. And for each of the 60, it will keep track of what's going on. So min will become 10, then 5, then 2, and so on. Max will become some value. Average will be some value. You'll have some You can maintain a sum field, a rolling sum, and then divide it by 60, and you'll have your average. So at the end of 60 seconds of computation, you will have min, max, average defined for that window of data. Then what the worker does is writes to cache plus database. And finally, what the worker does is commits offsets. So let's just go through this in a little more detail. So it will write to some cache and database. We haven't talked about it yet. We'll discuss cache and database shortly. Then once the write has been written out, what it's writing is this stuff, min, max, average, and perhaps some, it'll write timestamp or metric ID, min, max, average, and potentially some time window. For what window of time is the min, max, average calculated? That it can write something like this out. And finally, it commits offset. So offset is just the place where it computed in Kafka, what records it has processed. So place where it finished processing. So these are the sequence of actions in the worker, and where a streaming technology helps you, just detailing that a little more. So streaming technology like Spark streaming, the high level idea is you don't think of code like there's some end of flow of code. What happens is you write some code, there's some line of code at which basically all your actions are running in a forever loop. So Spark streaming processes are is basically a Spark application that will run forever. It has no concept of end until it dies due to some error or you kill it. It is supposed to run till eternity. And what it's supposed to keep doing is a sequence of actions you specify it to do on a subset of data, which is your micro batch of data. And these are the set of actions we have told it to do. So we will read, aggregate, write to cache and database, and commit offset. So this will happen on every read of micro batch of data. It will run these aggregations and keep preparing your aggregates and writing to your database and cache. That's how Spark streaming works. And these are the set of workers. So the workers will be Spark streaming workers, and you can have worker groups, like you can have a group of 3, group of 5. You can scale the workers up and down depending on load. It comes down to number of records in. If you are able to keep this somewhat consistent, then you know you are at capacity. Like number of records going into Kafka is number of records read out of Kafka. You know you are somewhere keeping a balance. The moment your number of records in is greater than number of records out, what happens is data is buffered. Data is buffered and growing, like it is accumulating in Kafka but not getting depleted from Kafka, which is not a good place to be. Ideally, you would like it to be this way, where records out are almost always going to be greater than records in. That way, records are always depleted. Worst case, what happens is Spark will ask Kafka for data, and there is no data to give, so it will just keep spinning and wasting cycles. But this is a better place to be because you are at least keeping up with the rate of production. But these are different scenarios, and how to solve these is you vary number of workers. If you increase workers, you are more likely to come into this bracket where you'll calculate process records faster. If you decrease workers, you are bound to get into this situation. But that's the rough math, and those are informed by kind of throughput and choices. You run the math and you figure out how things are holding up in real time. That's some discussion on workers. Any questions here? Deepak?
So Adityan, so here, in the step 1 and 2, so under the surface, is the worker basically waking up every 1 minute and going into the Kafka queue and reading those whatever 60-second worth of records and then computing this thing, or does it do it more often, right? Does it go back into the Kafka queue more often than 1 minute, right? To get this data, what happens?
I see.
In the Spark
I see where
stream?
you're going with it. So yeah, I wouldn't think of it like waking up. It's always up is how I would think of it. But when it's always up, you are telling it that when each pull from Kafka should be 60 seconds of data, which is 60 records. So in Kafka, we are storing 60 second level data. So each pull should be 60 records from the Kafka is how I would look at it. If you tell the worker I want to pull 120 records or 180 records, it is equivalent to pulling 2 to 3 minutes of data in one shot from Kafka. That's how I would look at it. And how often it does, I believe it's kind of it is. I wouldn't think of it as how often it does. It will fetch a record and then it won't go and fetch the next record until it's done processing the record it has already fetched. So, and it will keep growing I guess this might be useful to know. It will fetch 60 records, then it will queue 60 records to process. So what might end up happening is it can keep fetching, and you'll see it in Spark UI. There's a page on streaming. It will keep fetching, and then it will keep saying queued. It'll.
Oh, okay. So it keeps
it
builds a local buffer or something like that and keeps queuing into it, right?
Right.
So it's like your Roku device, right? Streaming data, and then it's like ahead of itself and processing.
Right.
Okay.
And each record you will see, in fact you will also see something like queuing delay, which will tell you how much time it took from the time it fetched it to putting it in queue. Then there will be processing delay as well, which will be something along the lines of how long did it take to actually finish what it needs to do with these 60 records. So aggregate and write to cache and write to database, all that stuff will include some delay, maybe 2, 3, 4 seconds. So there will be a processing delay. You can see all this on the Spark UI page, and it will keep track of where it is in the whole scheme of things.
And like when you said that you have to specify to the Spark streaming like the number of records in a window, is it number of records, or can it do it by time also? You can say get data for this much time, like for 1 minute or 30 minutes or whatever, or do you have to specify exact number of records it can window?
Yeah, I think it's closer to number of records, but it will be hard for it to figure out notion of time. But if you give it the window size in terms of records, it will fetch those many from Kafka.
Okay, thank you.
Okay, Animesh?
Yeah, I have similar question to what Deepak was asking. Like, because idea is we need to get the average within a minute, isn't it? Like, if you get 60 records, how do you know it's within a minute and it's not crossing a minute boundary? And the follow-up question is like, what happens if we drop some of the calls? Like, if we don't get 60 calls for 1 minute, but we get like 59 or 58? Does that mean we are going to the second minute boundary? Because I'm guessing we need to be calculating these averages for each minute, isn't it? Not last 60 seconds.
These are great questions. And it comes down to that whether you want very high integrity of data, or in the interest of big data, you're okay with partial miscalculations here and there. It can very well be possible that you may encroach the boundary of another minute with 60 seconds of records, because first minute only saw 40 data points and rest 20 are missing. So the remaining 20 came from the next minute. But because there's a big data scale system, one outcome you can potentially be okay with is, you can say that 60 seconds is what is immaterial, whether it got the true 60 seconds or those 20 seconds were spilling into another minute and whatnot. But in the interest of the big data system, it is performing well. And the number of occurrences of such miscalculations is small enough that it's negligible in your big picture system. Now, if you must account for it, then it will need a lot more strong guarantees of data and whatnot, which is much more difficult. And
or why not put these right rather than doing this aggregation, right? You're fetching this Windows 60 records and directly put it into some NoSQL Cassandra database. So you have these records, and then when you're pulling it, you just aggregate and give it back to them. Rather than doing this, right? You just pull the data, pull it into Cassandra, and then or any other database, and then when you're getting the report, you just do it. And there's no miscalculation at all. You don't have to keep a track of this. You're only thing what you're achieving is you're taking chunks of data and reading it and putting into doing a bulk insert into Cassandra rather than reading one by one queue.
The other thing you might be achieving is batch like pre-computing before. If you put it in Cassandra, you will compute aggregates on the fly. But here it's already computed, so it's a matter of fetching it from Cassandra or something. But if you put second level data, then when you load the dashboard, you're asking your system to compute the aggregate and return, which may be potentially slower as well.
Okay. Yeah, Adi, I think the time series database like thrives on these kind of a query, isn't it? Like right. I wasn't sure because I think I in my interview I mentioned no SQL database, but the right database for this kind of stuff is time series database.
Yes, that's right. That's right. Great discussion. Yes, actually, there's a talk from Datadog creators as well on how they store this data. There's a bunch of different technologies they use, some for quick retrieval, some for long storage, cheap storage, and whatnot. But yes, time series database show up a lot. And yeah, like you said, it's possible, but it's a matter of one more thing you're gaining is you're just aggregating before pushing it to whatever data store you use. So then there are no aggregation on the fly. But there you can let aggregation happen on the fly as well. And that can give you more flexibility, but potentially a little latency on your API response times. Having said that, we are coming up close. I don't mind waiting for some more time, but let's quickly go through cache as well. This was one part that we haven't discussed. So there is a cache holding 2 days of data. Let's briefly discuss how this thing is working and what are some strategies here. What is our cache holding? Its responsibility is to always be recent with 2 days of data. It gets returned to from your workers. How to keep it current for 2 days? How to keep it from going stale? Any ideas?
ETL or something in cache? ETL.
TTL of 2 days. That's a good answer. So effectively what we are trying to do is your worker will write to the cache, and this cache can be any key value store, and popular choices may include Redis or Memcache or something. But the end goal is you're going to write some key and value. We can talk about that in a minute. And you can write it with a TTL of 2 days. So each key will live for 2 days and get expired on its own in the cache. what are some, we have one big question to answer in our requirements, which is how will you query this data quickly? Like you want to query, we said 2 days of data should return fast. So how will you structure the data in your cache so that your queries return fast and are going to answer your kind of queries efficiently? Given server ID, retrieve min max average fast. Given metric ID, return it fast. How will you structure the data? Deepak?
I'm thinking.
Can we keep multiple caches?
You can have server ID and machine ID as key, and also machine ID, server ID as key, right?
Okay.
For the key value kind of pair.
Mm-hmm. You're talking about indexing on server ID.
Server ID and metric ID as key, and then metric ID and server ID as key, like two-way, right?
Great. So let me detail that out a little more. I think this comes up a lot of times in interviews on how will you, we talk about caching, but then if you delve deep into it, you have to then propose how do you plan to store the data in cache. So key value store, how will you fit your data in keys and values here? So if you, one way is you index on server ID. So your outer level key, one proposal is this, where your outer level key is a server ID, value is a hash map
of metric ID and
of metric ID being the outer key, and metric ID is the second level key whose value itself is a 3-value tuple, which is average, min, max, and this goes on and on. So you'll have 2000 keys inside here and 10,000 keys outside here because there are 10,000 servers. This is one way. Why is this good? Because now it gives you order one query time. So given a server ID, you query the cache, you retrieve it in order one for that server, and you'll get all the metric IDs in order one time, and you can return everything in order one. The other index you want to have is the other way, where given a metric ID, how will you answer those queries? So you want metric ID being the outer key, server ID 1 being the inner key, value being average, min, max.
And you should also have a timestamp here, right? Average, min, max, and some sort of a timestamp.
Right. Yes, that's right. 2 timestamp to figure out which minute, or you can just have number of minutes or something, because we are storing 2 days of data, and you can potentially simplify it just by minute of day or within those 2 days. That can be a simplification. But yeah, you will have timestamp as well, and you will store it in this fashion, and this will enable you to optimize your queries such that each lookup is mostly order of one time. Sometimes it may be worse, but you don't want order n time or anything like that. That will be too slow. So you want to keep it order one. And this is possibly coming back to the previous discussion we just had, which is now you already have this computed. So it gives you the ability to actually just look up your cache in order one time and return the results, as opposed to not having these values computed and putting them in some database at a second level data and computing on the fly. I think Prometheus or something, I believe from someone in the previous class said, does closer to that computation on the fly, while I think Datadog does batch pre-computation and returning results on the fly, something along those lines. There may be pros and cons, like computation on the fly can lead you to doing multiple granularities of data on the fly and so on. but it comes with latency issues as well. Okay, so that's a bit on the caching side. Any questions on this one?
But Adityan, the size of the cache is going to be a lot, right? In this case, if we do the computation, 320 megabyte per second, and we have to store it for 2 days. That's like terabytes of 32 terabyte of.
Why do you say so? Actually, cache size may end up being.
Oh, sorry. Yeah. It would be compressed, right? So it would be
Yes.
10 to the power 3. Yeah. You're right. So like
So
640
4
gigabytes.
bytes per this.
640 gigabytes. Yeah, something like
Yeah.
that. Okay.
Yeah. So 4 bytes per each of this, average, min, max, then 10,000 servers times 2,000 metrics times this is 444 is 12. So 12 bytes, actually 16 because you have a timestamp as well.
16.
So this might be one estimate of storage in your cache bytes, which is reasonable. And you can have many open source offerings, or even AWS has Elasticache, which is Redis, managed Redis. They offer managed Redis or Memcache. You can use some managed offering as well. That will take care of other issues surrounding cache, like how to segregate write and read traffic, all that stuff. But yeah, you can make use of some managed cache offering in this case. Last brief discussion. I think we are almost on time. So I know we talked quite a bit about time series data, but just a summary of the database choices that we are presented with. Time series databases definitely suit these needs well, but conceptually, let's just go back and answer these questions. Is it a read heavy versus write heavy traffic? Then is it a SQL or NoSQL database that is a good choice? And is the storage that you put in, is it row versus column storage in your database? Does anyone want to summarize what you think of these three aspects? Deepak?
Write heavy, no SQL, column storage.
Okay. Does anyone else have any other opinions? So I agree. Write heavy because it's getting written to by your workers. SQL versus NoSQL, your data will be potentially extremely huge, and NoSQL key values store kind of situation will help out with queries being much faster. It's also not very structured or anything, and we don't need to join data and all that stuff. Row versus column storage actually presents a very unique opportunity here, which is, let me just summarize this. Row based storage is each block is stored as a row, no matter how many columns there are, while column storage is each row of data is actually stored as different columns. Row storage is potentially faster for inserts, updates, deletes, because you're just writing one block of data. This is slower. Column based storage is slower for insert, updates, deletes, because you're writing 4 or 5 blocks of data, or as many columns there are. Column based storage is good for big data queries, because if you just query 1 or 2 columns, you can fetch just those 2 columns and exclude everything else. But most importantly, in this specific use case, if you see CPU data, and I'll wrap up with this, is CPU data will be highly repeated values, 12, 12, 10, 10, and so on. And there's only 1 to 100 possible values. So In such a case, if you opt for column storage, what you can do is you can compress this data very efficiently. You can compress all the repeated values to saying 12 occurred 3 times, 10 occurred 500 times, and so on. This is called run length encoding. And there are many encoding compression schemes possible, and column storage actually is very well known for helping you compress big volumes of data efficiently, especially even more given that our data nature of data is only 1 to 100 for each value. We can kind of utilize the compression techniques column storage gives us to compact our data and pass on that cost savings to our customers. So conclusion being, database choice will be informed by many of these, and there are many vendors for each of these. Someone said InfluxDB. You can look up why InfluxDB is a good choice, but perhaps it has 2 or 3 of these characteristics. It's NoSQL, and perhaps it's columns-based storage and whatnot. So there might be different vendors who do many of these things. Their competitive edge is to build those products, but given the nature of data, what we know, and the rate at which we'll query, we can kind of inform our choice of database technology from there on.
So Adityan, what will you prefer in this case, row versus the column storage? The row is like, as you said, faster inserts and updates, but do you think row makes more sense than column?
In this case, I would still prefer column storage. But that being said, I think when I looked at Datadog's talk, the true answer is both for certain use cases. In this case, how I see it is faster insert updates. It's potentially a little slower on the right side of things to go with row-based storage. But perhaps the compression value of storing that data in column storage outweighs that slowness in write, because at the end of the day, you want to find a balance of performance and cost. You will price Datadog accordingly, and one way to price it competitively will be to reduce your cost of storage so you can beat the market and whatnot. So that might be one way to look at it. And I can link the Datadog talk. They do a host of many things. There's no one answer or one technology they actually end up choosing.
Yeah.
Actually, this one is the talk, building real time.
That you have to make for.
So they actually, okay, I have that slider as well. So they choose all these different kinds of storage techniques with capacity, latency, cost, and they have many other choices they make. This might be a good talk to look at post this class, since we delve deep into this discussion.
Can you post the link, please?
Yes. Okay. I don't mind waiting for 5 more minutes. I will have to drop soon, but happy to answer any other questions, content or interview wise, anything else that I can be of help to you all. Here's my email as well. And yeah, thank you for your participation and questions and feedback. This was definitely a useful time for me, and I learned something new as well, but hopefully you all also took away something valuable from it.
Thank you very much. It was a wonderful class.
Thank you.
Thank you so much for your knowledge. Yeah.
Aditya Kavi here.
Yes.
Aditya, I was just thinking, like, by just choosing this time series database, this can be much more simpler. I'm just thinking, like, because currently we are having two kinds of JSON structure. One basically for the metrics ID, and another one is basically with this server ID, right? And that is what we store in the cache layer as well, right?
Right.
I don't have much experience on the time series database, but what I'm just looking at, in many places they have mentioned about time series database for these kind of use cases. I was just checking one of the book where it is mentioned that all these these kind of use cases, metrics monitoring and alert systems, they all use time series databases like a Datadog, InfluxDB, a New Relic, Graphite, Grafana. All these people, I think they use time series database. So I'm kind of so do we need to learn more and then propose a time series database is going to be helpful, or we will go with this? Because since we don't have experience in time series database, a better way to approach this interview is basically proposing these kind of structure and keeping them in cache and database like NoSQL DB, because I have experience with NoSQL DB.
Great point. Yeah. So I would say if you open the door with some specific technology, I would be ready to defend any probing questions on that. So if I have personally haven't worked with InfluxDB, so I wouldn't really make it like a strong candidate there, because then I know the follow-up questions will be on things on how InfluxDB works and internals of it. So if you are comfortable with some time series database, I would choose them. Or the other option is you can learn one time series database for such questions and know the in and out to defend those questions that will come up. Or generally, you can conceptually say that your choice will be a NoSQL database with column storage and things like that. That may be a safer way to play it. And add professional experience if you have with them, you can mention them.
Yeah. I think maybe we can propose a NoSQL plus cache, and then again we can talk about the time series database, but we can genuinely say that we don't have much experience on that part. Right, because I see that a single query can solve this issue in time series, because I am just seeing that query as well. So I'm not very sure how powerful these database on for these kind of use cases. That is only thing.
Great.
Anyway, thank you so much. It was a wonderful class. Thank you so much.
Thank you, Kaviraj. Deepak, did you have something to share?
Yeah, Aditya, one question I had was in the cache, would you still store the full 2-day database or 2-day data, or would you cut it down to like 20% of the estimated data volume?
Oh, I see. How I look at it is there are two kinds of cache. One cache responsibility is to always have 2 days of data, whether you're going to query it as much or not. The other kind of cache is potentially what you're talking about, which is if you query the same thing again and again, you want to store those things in that cache to return frequently asked queries quickly. And that cache can incorporate storing data size of some less reduction or something to be more space efficient. But if you want to have 2 days of data available, that can be sitting in one cache with the entire 2 days.
Okay. Yeah, makes sense. I think in this case, because it is time series, so you want to keep the whole 2-day data.
Yeah, exactly.
Okay, thank you.
Great. Thank you all for your questions. Thank you. Good luck.